Hi, everybody. You tell me when it's when you're good to stream.
Hello.
Hi. So good morning, everybody. I hope you were able to rest from last night's talks and cocktail. We're starting as soon as we get the go. We're good. So, Carla, take it away. Present yourself and take it away.
Okay. I'm sorry. I want to start. Hello, everyone. I'm Carla Raffles from Universitat Pompeu Fabra, and I will tell you about some work we've been doing with Alexandros Zakarakis, who's here, and with Nikitas, who's also here. And thank you, everyone, for showing up so early. Okay. So, holography accumulation, it's a fancy title. I realized that when I was preparing the slides that I was not using the word holography, so I will try to explain what's the title, so if I forget, tell me. Okay. Okay. Okay, so this talk I will give you some introduction to SNARKs and a motivation of the research problem we're trying to address here. And I will show how the ideas we have, very high level, how they apply to recursive proof and to privacy-preserving delegation of SNARK provers. So this will be, okay. So as you know, when we want to prove something with a SNARK, we have to represent computation in a certain way, okay? So here, a typical statement we might want to prove is circuit satisfiability. Here we have a small circuit, and we want to prove statements maybe of this kind. We want to show that the circuit evaluated on some certain public inputs, which are the X, results into some certain public output. This can be abstracted in a more general form into this R1CS rank 1 constraint system, which results in a system of this form where this dot stands for the Hadamard product. And I like to think of this kind of constraint system as proving three things at the same time. So it's proving that there have some public input relations, that there are some Hadamard product relations. So if you look at this circuit, in fact, what we are trying to prove is that there is a certain multiplicative relation between the left and the right outputs, inputs of the multiplication gate. So A are the left inputs, and B are the right inputs. And there is some set of linear relations that we want to prove. And for this talk, so for this talk, what I'm interested in highlighting is that these matrices, as you probably know, they are all sparse. They are big because they depend on the number of multiplicative gates, essentially, and some inputs. So here you have like the matrices that would result from this proof system. Okay, so they are sparse, but they are large. Okay. Okay. Okay, so if I do like that, it means change. Okay, so here you have an example, okay? And this generalized... Sorry. Okay. So, 2, please. One more? Okay, thank you. And this generalizes, like if you want to use more flexible constraint systems, because this allows you to reduce the size of the constraints. This generalizes to these customizable constraint systems, okay? As you may probably know, this comes from generalizing some way of writing constraints that appeared in the Plonk proof system. But it's essentially the same, okay? We want to prove these three things. Public input, Hadamard product, and linear relations. And the thing is that there's like a very, like as you probably know, when we want to write, want to prove things with a snark, we want to write all these linear relations as some kind of polynomial identities. And the interesting thing is that actually all these things we want to prove, like public input, can be done, sorry, can be done by encoding every vector as a polynomial, and then you can see there's like a certain polynomial identity that maps public input, Hadamard product relation, and so on. But maybe you have not, like the only way we know how to prove linear relations is essentially we know how to prove one linear relation. We know how to prove an inner product relation in this polynomial identity. In fact, we want to prove like many linear relations, right? Like we want to prove that A Z is equal to the right output and so on. So how do we deal with this? Well, this is like a different way to classify proof systems and how do they deal with this problem, okay? You want to prove many linear relations, but in a non-interactive way, directly mapping these to polynomial identities, we only know how to prove one linear relation, which is one inner product. Okay, and then you can like think of systems like Plonk, hyperplonk, and so on. They are like permutation-based arguments. So in some sense, what they're doing is they don't prove R1CS, but they write the constraint system so that these matrices that appear that they have to prove are permutations. Okay, and then they use some identities between polynomials that, this is simplification, but essentially there is a way in which you can prove that something is a permutation. And then there's like another family of proof system, which are Marlin, Fractal, Spartan. I'm basically talking about univariate polynomials, but like it's essentially the same for the multivariate case, okay? And these proof systems are lin check based, okay? So what does it mean? So essentially when they want to prove like many linear relations, what they do is like they collapse, they get some random vector that comes from the verifier, and they collapse this set of linear relations to a single linear relation, okay? So we have this if and only if, where it's actually not an if and only if, this is with high probability, okay? So if the left side is true, if and only if this, so this becomes one inner product, and this is also an inner product of one vector, okay? So this is one vector in the row space of the matrix M. My point in this talk is that, well, there's a significant difference between these two different ways of proving linear relations, and one is that when you move to this kind of way of proving this permutation-based proofs, everything is private computation, okay? Why? Because if you want to prove, you're essentially proving that the two witnesses have a permutation of each other, so you need to know the witnesses. Whereas here, there is like a certain part of the computation that is public because you're proving two things, okay? So you first prove that the inner product relation is satisfied, and then you need to prove really that this vector, which is a vector in the row space of the matrix, is correctly defined. And this is something that actually the verifier could do himself because the matrix is public, it's part of the description of the circuit, but if it does it, then it's like the matrix is too big so that the verifier cannot really do that. Okay. So the main point of this talk is saying, okay, there are advantages for using this, for this way of proving constraints, both in recursive proof composition and in privacy-preserving delegation. So So this is like maybe one of the main messages. There's like another message, but like, yeah. So yeah, okay. So if we look at Lin-Cheng-Bake's argument, like we look at Marlin, for example, we have that we can divide it conceptually like something like this. In the first part, like there's a commitment to the witness, and then you get some challenges. And then in this outer sum check, you prove, you do some, you just send some terms that serve to prove all these polynomial identities that I said in the beginning, no? The public input, everything. Everything that is succinct. Then you get a challenge, and then there's like this part called the inner sum check, which is actually devoted to proving that this public computation is correct. Then there are like opening polynomials and so on. Okay, and actually the verifier predicate can be split in 3 parts. Okay, so there are like some succinct checks that the verifier needs to do, then it needs to check that the polynomials are correctly open, and then there is this orange predicate where the verifier is trying to show that this public computation is correct, okay? If you eliminate this is also a snark, but then it's like a snark with a linear verifier, because the verifier has to check this himself, okay? Next. Okay. So the point is that this part, okay, is relatively expensive. Okay, this is something that's like, and this is like where I have to remember to explain the title of my talk. Okay, this relates to like this part can be avoided, but then you get like a linear verifier. It's not a pre-processing snark where the prover, where the verifier can check everything succinctly. Okay, so it's like related to, this part is related to having this thing called holography, like, okay, a certain way of pre-processing the computation so that everything can be succinct. It's significant because the cost of this thing is essentially in a large, I didn't mean to say O of k MSMs. I mean to say it costs something like a linear number of group operations in K, where K is the sparsity of these matrices. Okay, it's the maximum size of these matrices, which in reality it's a small constant. Probably it's 1.5, 2, and 3, but it's still a good portion. Okay, and then it also means K log K field operations. Asymptotically, if you look at the cost of this, it's not fixed, right? Because it depends on the matrix. It's not like a fixed portion of the total computation. And like if you look at Marlin, even like how you prove later that this thing is correct means you have to have like a large degree SRS, okay? It's something 6 times K or something like that. Okay. And I want to say that, sorry, I want to say that this overhead, if you look at things like fractal, which is like some essentially Aurora, like is a hash-based proof system, which is essentially like Aurora, where you put like a succinct verifier. You can see in their experiments, this part is this public computation part is not negligible. Okay, so how do we apply this to recursive proof composition? So let's think of incrementally verifiable computation that I'm sure almost everyone in this audience has heard about before. So essentially, we have like a computation, and we're dividing it into small, we're doing it incrementally, so we're doing like one chunk at a time, okay? And then it's like at each step, it's like a non-deterministic computation. There's like a certain input and so on. So in each step, we want to make sure that some certain relation, some function of Zi is equal to the next evaluation. So the way people introduce verifiable computation, the idea was like, okay, so what we will do in each step is like prove that the computation is correct, so that the function f really is evaluated correctly, and also give a proof of a proof that the proof of the previous computation verifies. Okay, so when we have like a prover, It basically has two parts, okay? On one hand, the prover, this is the prover that is executing each of the steps, is trying to first check that the function is correct, and then it will prove that this circuit, which is the verifier of the snark, okay, evaluates to 1, so that the proof verifies. And then there's been like a series of works, starting by Halo, then formalizing this accumulation notion and folding and so on, where the idea is, okay, like the problem is that this prover becomes really expensive because like the snark prover is not cheap in the first place, and then you're putting inside the verifier, which means like you have to arithmetize you have to create a circuit that represents the verifier, and this grows like quickly and very much when, because of the type of operations you're doing with the verifier, okay? So there was this idea, okay, what if some part of the computation is deferred, okay? So what if the prover doesn't execute the full computation, but keeps some part for the end, and at each step, the sum of the computation is accumulated, okay? So it means like you have to prove a certain relation inside here, so the idea is instead of proving it, you just batch all the statements you want to prove at each of the steps, okay? So essentially it's something like that, okay? In each step, the name folding is a bit confused because it's used in different ways, but essentially the idea is, okay, there is a part of the computation that we don't want to do, we just want to batch it together with similar computations, okay? In a way that, which has like these properties. So if the final computation, if the final statement is true, then the other statements are also true, okay? So the claims are accumulated into one final claim. Okay, and so what is the state of the art? So that people have applied this idea to build IBC in different ways and contexts. So first we had like this idea of full recursion, where like all the computation is executed at every step, the verifier, like the full proof is checked at every step, and so on. Then there was this notion of atomic accumulation, which the proof is completely computed, so the prover is fully executed, but some part of the polynomial opening is not fully checked. And then finally we have this notion of folding and split accumulation, which what it's doing is like pushing this approach to the limit. No? So it's like essentially the verifier doesn't check anything, it just checks that these checks are accumulated correctly, okay? So that all the computation that is deferred is like correctly compressed to a new step of computation. Yes, and okay, so next. So we have something like that, okay? So for this type of snark, the yellow part is what is executed. So everything is executed, everything is checked. Here, everything is executed, but there is a certain part that is actually also public that is not verified. And here, we have that only this part is executed, okay? And all you verify is that the computation is collapsed correctly. So, one important difference between these two and these two approaches is that here, actually, there is some private state that needs to be passed to the rest of the computation, right? Because you are essentially not proving anything, and at some point you will need to prove things, and at the moment where you need to prove things, you will need to be able to know the witness. Okay, so our point, like this is what we do in our paper that I hope to put in preprint next week, is to revisit this an approach introduced by Darling, actually in some ZKProof, where what they suggested is like this part, this orange predicate that checks that the public computation is correct, is not, I have 6, okay, is not fully executed. Okay, and so it's essentially what is the prover that it executed is everything except this part, okay? And then this predicate is like deferred to the fact, proving this predicate is deferred to the end, okay? Sorry, I forgot. I want to say that this is also like, here there's also no private state that is passed to the next computation. Okay. Next, please. Okay, so that's our results that we will put on ePrint. So we revisit this proof system. We make it slightly more efficient and show how to generate to multiple state. And I think here, like the point I want to make is that I think that's the really important point, is that I see no reason why you should ever use full recursion, okay? So like, so full recursion is like slightly, like this is also like a relatively expensive approach because most things are checked, but yeah, okay, but anyway, like that's the point of the, I'm trying to be fast now and it's going too fast, okay? So that's the main, one of the main takeaways, okay? Like, don't use full recursion, use this type of accumulation. And finally, we have other results like showing that how to prove this part of the computation independently of the sparsity of the matrix using inner pairing products equation. Okay, so last, I have 5 minutes, no, 4, 3. Okay, my timer doesn't say. Okay. Okay, so the second application is to privacy preserving delegation of computation. In general, there's like several works that are trying to do this now. And like what we want is to, computing as an arc is relatively expensive, so like we can think of delegating this to a set of provers. Why? Well, because the person delegated, the user, doesn't want to give the full witness to everyone. So like with the research question is like, okay, can we think of amortizing some of the work, given that this, like, assuming there is like a server that is doing computation for many people. Okay, so please. So, and then because of this, we again focus on this Marlin proof system where we remove this part, like the linear check, the link check, we split it in two, so we don't prove this part. Okay? And that's actually the witness-dependent computation part. The rest is witness-independent. So intuitively, we can think a scenario where this part is executed locally, and the public part is delegated to some computation server that executes these proofs. And the thing is that actually that's very convenient to delegate because there's like, this is like a constant size string. So anybody can do that, but this server just like it's relatively expensive. This server can do this for you. And then later you just can check a full proof, but verifying these two parts of the proof independently. And the idea that we propose is to amortize this public computation. There's a server that is doing it for many people. How can you amortize it? And then we think of this orange server that's doing all this public computation as something like this. So now you can move 5 slides, please. Okay, so it's getting statements from many people. It accumulates, it sort of like folds and aggregates all these statements into a single one that he sends to the parties. And then it just proves this one single statement. Okay, this would be an idea. So what is missing in this approach? Well, the users, they need to receive a proof that the final aggregated statements included their own statements, okay? Otherwise, they will think, they know the proof that the last statement is true, but they don't know that their particular statement is included in the proof, okay? So they all get, like, we can think that they all get a proof that their statement was included in the final proof. What's the problem? that if you will do apply this solution naively, then each of the provers will know everyone else's statements. That's something we don't want, like, okay, because it doesn't make sense in this scenario. So what's the solution? So the solution is based on a paper we had with Alexandros years ago, which is folding scheme with local verification, okay? We have several users, we build a tree, so we aggregate all their statements, and the nice thing is that actually you can verify, it's like a Merkle tree sort of approach, okay? You can verify that your statement was included in the final aggregated statement in a sublinear way by just getting a path of aggregated statements. So this is the final slide. So what do we achieve with this approach? We have like a trade-off between the cost server who's trying to compute on the proofs and the complexity of the verifier, right? Like each of the individual verifiers will pay some little extra cost, so which is this. So each verifier will check that the private computation was correct. It will check that this final aggregated statement is proven correctly, and then it will have this small proof, which is the small proof that says that his statement, it was correctly included in the final statement that you want to prove. Sorry, too many technical problems. Okay, and that's it.
Big applause for Carla. Thank you, Carla. And sorry for the small rush there. Do we have any questions?
So in the delegation idea is really nice. Can you repeat I didn't understand exactly what is the work that's left for the client to do? It seems like it's still not constant.
No, it's not constant, but like the point is that it's two different things. Okay, there is like this witness-dependent computation, and this part is the part that you should delegate. So either
witness
compute
witness independent, you delegate.
No, so you delegate the witness independent part, and this is amortized. And then there is the other part. Right. It's not constant. It's cheap. It's like something like dominated by 5 multi MSMs, like witness side. And this, like the point is that these you can distribute independently. Mm-hmm. So, I mean, actually, that's a good point. Like, you had this paper with Ozdemir, no?
Yeah.
And you investigated how efficient was it to do MPC for computing these NARCs. And, like, one of the conclusions was that Marlin was more MPC friendly. And this confirms these results, but also says, like, I guess that really the computation that you need to do Windows independently is like minimal.
I see. So the MPC really only have to be applied to a small part of the computation, not all of it.
Which I guess like people do it indirectly because maybe they already take these into account. But like I think, like with this approach, the total cost proof is something like when you divide it by the number of proofs, is something like 5 MSMs in total.
Yeah. Very cool. Got it. Thank you.
Thank you. I actually remember when Dan spoke about accumulation schemes in a previous older ZKProof. So it's good to see that the idea continues. Thank you again, Carla. We're now gonna hear from Michael Adjedge on optimized ZKProofs for Pali-based 2PC ECDSA. Thank you, Carla. You can give it to Michael straight. I just want to apologize for the kind of pressure at the last minute. I know that the schedule says 30 minutes, but that includes like a 5-minute sort of Q&A. So I just want to make sure that all the speakers are reminded of that. So you have 25 minutes and then 5 minutes. That way we have for 1 or 2 questions at least. Are we ready? So you're also, okay, good.
Yeah? Okay. So, hello everyone. I'm Michael Ajed. I'm an applied cryptographer from Fireblocks. And today I will present the results of our work with my co-authors, Kosti Bloch, Geoffroy Couteau, Arik Galansky, Antoine Joux, and Nikos Makrianis, titled Optimized ZKProofs for Pi-based Two-Party Computation, ECDSA. The full version can be accessed at on the ePrint on the link below. What will guide us through this journey is the following plan. First, I will start by explaining what motivated us to work on this subject. Then I will talk about the protocol itself. I will continue by introducing new techniques that we used to make our protocol faster and more efficient. And I will conclude by listing some open questions and future work. So let's start by the introduction. So you have to know that trillions of dollars with a T were transferred on blockchains, and most of these transactions were signed using ECDSA, and at Fireblocks alone, we secured around $6 trillion using our MPC ECDSA solution. So this makes it a target of choice for hackers, especially last February, an attack happened and more than $1.5 billion were stolen on Ethereum. In average, blockchains see millions of transactions per day, and so they need to be highly secure, and we need to avoid single point of failure. So it seems that threshold ECDSA is the way to go. Just a thing, the screen here doesn't work. Is it normal? Anyway, that's okay. So what do we want for the ideal solution for cryptocurrency wallets? So as always, we want it to be fast. Great. Oh, it's okay. We want the communication between parties to be small, and by small, ideally, we want it to fit into a QR code to allow offline signature. There is something else for MPC protocols. We want the number of rounds to be optimized or minimal, because each round between parties induces latency, and our benchmarks showed that for two parties in the same region, for example in Europe, we see an average of 35 milliseconds latency before even including the data that is sent. And between two different regions, it can go up to 150 milliseconds. And there is one last characteristic that we want, that we call concurrent security. In short, we want the parties to be able to sign many signatures in parallel without compromising on the security. And by millions of signatures, I say it can be using either the same key or different key. So let's look at the best-in-class solutions for two-party CDSA. We can see that the first one, Lindell 17, clearly outperforms all the others in terms of computation or communication, but it lacks in terms of the number of rounds. And we saw in the last slide that in this case, this becomes the dominant factor. Also, it does not offer the concurrent security. And all others basically lack in at least one of the characteristics that we want. And okay, and our solution, yeah, one more. Our solution stands there, so we were able to achieve it in 2 rounds of communication using a reasonable amount of communication and computation. So I would like to first apologize to all of us. I know we are at ZKProofs, but I will not talk only about ZKProofs. Don't worry, there will be some. Especially, I will not talk about all the zero-knowledge proofs that we use in our protocol, but I will also focus on some optimizations that helped us making our proof generation faster. That's okay. So let's talk about our protocol. So a quick reminder about ECDSA. It consists in 3 algorithms. The first one is the key generation, where we sample a random scalar and compute the associated points. Then we have the signature on the message using this formula, and at the end, the verification, where we just check that this equality holds. And what is a two-party ECDSA? So we have Alice and Bob. They both have a share of a key, of the secret key, and they want to sign a message M. They will call the MPC ECDSA functionality, and at the end, they will get the signature as if it was signed by the recombined key. In practice, this is done using rounds of communication between the 2 parties until they get the signature. So our solution works best in this configuration that is called a star-shaped topology, where we have one server that serves many clients and want to sign transactions with each of these clients, each of them sharing a different key, of course, with the server. This is typically the case for cryptocurrency wallet providers. So the 2 parts of our protocol. The first one is the key generation. This one is fairly simple, so I won't go into the details. Just know that it's an additive split. So at the end, the recombined key is just the sum of the 2 private shares. But the most interesting part is the signature generation. You will have to click many times here. Sorry, Daniel. So after the key generation, they both have a share of the key, x1 for the client, x2 for the server. But also the client knows the public share, uppercase x2 of the server after the key generation, right? So during the signature generation, the server starts first. It samples random nonce k2, compute the associated point R2 and Y. Basically, Y is a proof of knowledge of K2, and it sends everything to the client. So the client checks that the proof verifies, and thank you, computes her own private nonce K1 and the 2 associated points R1 and R. And then it sends it to the server. So in this case, R becomes a proof of knowledge of K1. So the server checks it, and if it verifies, it computes the x coordinate. It extracts, I should have said, the x coordinate of the following point. So it's basically R, but shifted with the output of a random oracle. The client does the same on her side. Well, the 2 points look different, but trust me, well, it's very easy to see that they are the same, right? But not only, the client also computes the 2 following values, A and B, and from this point, they can call an OLE oracle with all these inputs, and at the end, the server gets the value Y. And I know that we not easily trust people in ZKProofs, but you have to trust me on that. This becomes a valid signature on the message M, as if it was signed by the recombined key. So what is an OLE oracle, or oblivious linear evaluation? So we have 2 parties, Alice and Bob. Alice has secrets A and B. Bob has secret X. And the OLE outputs Y to Bob such that Y equals A times X plus B. And we also want that no one learns anything about the secrets of the other party. But this was not the OLE I showed you. I showed you this one, the modified one, which takes an additional input point on the curve X. And in this case, you're too fast for me. And in this case, the OLE outputs Y if and only if the secret of Bob is a discrete logarithm of the input point. So how to instantiate such an OLE? We have many possibilities. One of them is to use an additively homomorphic encryption scheme, which has the following property. So we can basically compute an encryption of the sum of 2 messages, M1 and M2. Slowly. by combining an encryption of M1 and an encryption of M2. And we have also like a consequence of it, which is the multiplication by a constant, where we can compute an encryption of M1 times a constant by, again, combining the constant itself with an encryption of M1. So the instantiation of the OLE is quite straightforward, using the two previous properties and the following formula. So this is secure only in the honest but curious setting, but we have to deal with dishonest or malicious user. We'll see it in a minute. And last question, okay, in practice, spoiler, how do we implement such an OLE? Well, it was written in the title already, so you already know the answer. We will use a PIE crypto system, which consists in 3 algorithms. The first one is the key generation, where we sample a biprime, basically. The second one is the encryption. It uses this formula, and the last one is the decryption, using this formula as well. But it's not only this. We will use also 2 additional zero-knowledge proofs that we adapted from ZKProof 20. The first one is called PyMod. It basically proves that n is a biprime, where each prime factor is congruent to 3 modulo 4, and also that the GCD of n and phi of n equals 1. And the second proof that we call PyFac proves that n has no factor larger than the square root of n times a small, quote-unquote, constant. Notice that I haven't said the prime factors for the second proof. I only said factors. Well, it has an impact on the prime factors themselves, but just to be noticed. And, well, the instantiation is very straightforward. We'll use these amazing 2 properties of PIE crypto system. We'll also use the 2 proofs that I talked about. And to instantiate the modified OLE, so the one that takes the additional point as input, we just need a proof of knowledge of the discrete logarithm. And this proof of knowledge only needs to be done during the key generation. Okay, no need to do that during the signature. So let's dig a bit into the PyMod proof. So the one that proves that n is a biprime, well-formed, and that the GCD of n and phi of n equals 1. So we have 2 parties, the prover and verifier. The verifier starts first and generates a challenge y. The prover then computes or determines the 2 unique bits a and b, such that y0 is a square modulo n. And from this, it computes the 2 following values. First, x, which is a fourth root of y0, and then z, which is nth root of y. And it sends everything to the verifier. And the verifier, well, it does its job. It verifies. Basically, it verifies these 4 things, that n is congruent to 1 modulo 4, that n is not a prime number, so it's a composite one, and that the 2 last equalities hold. Go back. So this proves, so I said we adapted it from ZKProof. The original proof had a soundness of 1/2, so it had to be repeated many times, a number of times on the security parameter. We improved this one, and now the soundness of this proof, following some additional properties on the factors of n, has a soundness of 1/4, so it has to be repeated only twice as less. So how to deal with dishonest or malicious parties? So as I said, we made use of many zero-knowledge proofs everywhere. First in the instantiation of the OLE, but also during key generation. During the key generation, I said that we used a shift which is derived from the output of a random oracle. It was mainly to deal with dishonest nonce generation by the client. And when we need so many zero-knowledge proofs, well, in our case, we had to deal with many algebraic structures. We had to deal with modular integers. We had to deal with elliptic curves. And in such a context, the go-to technique is to use integer commitment schemes. So we decided to use the Damgard Fujizaki one, which is very simple yet efficient. And we need it for both the client and the server. And also, we needed to prove that the parameters are well-formed for the soundness of the proof. So let's think a bit about the Damgard Fujizaki commitment scheme. So first, we have the setup, where we sample a product of strong primes. Okay. We need a quadratic residue modulo n and two secret exponent lambda1 and lambda2 and compute the two associated values u1 and u2. And then the commitment is as follows. It works, we took the two commitment schemes. So we commit on two values and it works as follows on M1 and M2. We first pick a randomizer row and compute the following value C. Notice that the party who commits using this scheme is usually, or at least in our protocol, not the one that generated the parameters. So it needs to be convinced that these parameters were well formed, and for that, well, we used zero knowledge proof, which is the following. So, well, it's a very basic Sigma protocol. The prover commits to a given value. The verifier sends two challenge bits, E1 and E2, and the prover responds to it, answers to it. And then the verifier checks that this equality holds. So now, if we look at this description of the commitment scheme, we can see few pain points, and they are of many types. So we have either a computationally intensive operation or bandwidth consuming. Because if we look at this proof, it has a soundness of 1/2 as well. So it has to be repeated many times, and once it's sent, well, it consumes as many more bandwidth. So we have a few of them. First, we need to generate strong primes, which is a quite costly operation. And then we have a bunch, you can click a few times, a bunch of exponentiation for the setup during the commitment, but also during the zero knowledge proof, twice again. Yeah, once. And yeah, as I said, sending the proof is bandwidth consuming. So we'll see now in the following slides how we dealt with all these pain points. So I will now introduce a few additional techniques that we hope will be of great interest for the community, and that will help everyone improve protocols and make them faster and more efficient. So I would like to start by introducing a new class of prime numbers that we call TAF primes. Before explaining what they are, just let's recall what are strong primes. So they can be written this way, 2 times P0 plus 1, where P0 is also a prime number. Now, to define what are TAF primes, we need a security parameter L, and TAF primes can be written like this, 2 times the product of smaller primes Pi plus 1, where each of the Pi is of length 2 times the security parameter. So this is to the best of our knowledge, this is the first time that this class of prime numbers is proposed, and we claim that they offer identical security guarantees than strong primes in at least all of the use cases that we use in our protocol. Well, we have, it's backed by some arguments in our paper, so I encourage you to read it. But what is even more interesting about TAF primes is their generation. We use this algorithm, which is fairly simple. First, we sample a pool of small primes, and by small I mean at least two times the security parameter. And we pick a random subset of such primes, multiply them together, multiply by 2, add 1, and check whether the result is prime. And this gave us the following numbers. And we can see that when we compare the generation times of TAF primes versus regular primes for the size of 1.5 kilobits, we only lose a factor of 1.4, while when we generate strong primes, the factor is around 50. And the factor is even better for bigger prime numbers between tough and regular primes, and much worse for between strong and regular primes. So we applied this new kind of primes to our Damgard-Fujisaki use in our protocol. We applied it for both the client and the server, and we saw a 15x improvement for the key generation. Oh, it was really crazy. The second technique I want to talk about, how many? Okay. I want to talk about is the short exponent trick. So we have this problem, the short exponent discrete logarithm. It's a quite well-known problem, quite well-studied. In short, it says that it should be hard for an attacker to solve the discrete logarithm if it was generated using a short exponent. We have a second related problem, which is called the short exponent undistinguishability. Basically, there is only a negligible advantage for the attacker to distinguish between something that has been generated using a short exponent and something that has been generated using a full-size exponent. These two are related. It has been shown in KK04 that SEI reduces to SCDL in the case of prime order group, but we also showed that this reduction is true in the case of unknown order groups. And we applied it to the PIA encryption in the following way. So this is a reminder of what it looks like, and the thanks, Diane. Perfect timing. And the most intensive part is this one, okay? It's an exponentiation using n as an exponent modulo n square. And we notice that if we pick rho, the randomizer, as already a square modulo n and already raised to the power of n, it can be a constant of the PIA parameters. Of course, it has to be checked by all the parties. And then the encryption is done as follows. We simply need to sample a random exponent r of, well, small, of the size 2 times the security parameter. And, well, it's clearly faster because the computation time of the exponentiation is linear in the number of bits of the exponent. And of course, it's still a valid ciphertext, okay, because the right part of the ciphertext still vanishes once raised to the power of phi of n. And this gave us the following numbers. So we saw 15x improvement for the with a PIA key of size 4,000 bits. You remember these slides? Well, we solved everything, right? The first one on the top left was solved by replacing strong primes generation by tough primes generation. And all of the others were solved using the short exponent trick. We just had to pay attention to these two following operations because they were used to statistically hide some components. So they couldn't fully benefit from the short exponent trick, but still we were able to optimize them a bit. So let's now jump to the conclusion. I'm right on time, apparently. So you have to know that this protocol is currently under deployment for a real-world application. It's also being audited, both the code and the protocol. Once the audit is done, we'll publish it, we'll make it available in this repository. It will be completely open source, free of charge, whatever. You can do whatever you want with that. Then we would like to know whether it's possible to even further improve this protocol. Can we even lower the communication, the computation? For example, there was a paper last year that showed how to combine the PIA with the Damgard-Fujisaki integral commitment scheme. So if we combine them both, we can reduce easily the computation communication. So we need to know by how much, how fast we can go, and so on. Wait a sec. And of course, the tough primes thing. So we we gave strong arguments in the paper itself about their security. but we still want to know more. What would be the implication regarding security if we use them everywhere where usually strong primes are used? And, well, I hope that you enjoyed the talk now, and I think it's time for questions.
Thank you, Michael. Do we have any questions? Yes? No? There were two almost questions. Oh, there's one at the end.
Yeah, thanks for the talk. It looks like it's all applicable also to end parties and threshold protocols, right?
So maybe this should have been another bullet point in the previous slide. There is a way quite simple to virtualize the client, so that the client, instead of being one physical party, will be many, and it can be thresholdized quite easily. So this would be n+1, because we cannot virtualize the server as easily. So yeah, there is a way. We haven't looked more into that, but we strongly believe that there is.
Thanks.
Thanks for the question.
There's time for one more question.
Thanks for the great talk. One quick question regarding the intuition behind tough primes. Could you, if possible, could you tell us a bit more about how you came up with that definition?
How we came up with the intuition that they are as secure as strong primes? Well, we looked deeply into the state-of-the-art factorization algorithms and also discrete logarithm solving algorithms. And we saw that, well, nowhere it gives an advantage to the attacker, like the form of the prime gives an advantage to the attacker compared to strong primes. So, but again, some of my co-authors are already working on it, and hopefully they will have a paper soon, really a deep study on that and all the use cases. But there are already a few arguments that you can read on the paper. I don't remember, to be honest. They are very theoretical, but few things are explained already. Thank you for the question.
Let's thank the speaker once more. Thank you, Michael. Before getting the next speaker, I just want to add a second apology. I know this morning is starting a little bit with some batches. For the click, of course, in a room full of cryptographers, it seems like there is some kind of interference of the signal that doesn't allow the click in signal to get there, but we're going to try again just now. So we're now going to hear from Helger Lippma, and please try to see if you're... Oh, Michael, where did you put the... Here? Here. It's here. So, I think it may work.
It may?
Yeah, just try.
Move
Try
the
it.
computer now and change something.
Come on, like I told you, from the top kind of thing.
Okay, let me try.
Just the left and the right. Yes, there you go.
Is it working when you don't do this?
No.
No, this doesn't.
That on the top works. You see, with an angle, we managed to get away from the interference.
There is a spy in this room. That's going to be interesting.
You're good?
I don't know.
Let's try.
I have no idea. At least it's not going to be my fault. So, hi, I'm Helger Lippma. I'm from University of Tartu in Estonia. And this talk is called Polymath, Grot 16 is not the limit. The paper was at Crypto24, so it's already a bit old. But also, to be honest, the results are back from 23, so it took a while to get it published. So I think the first slide is very, I don't have to explain it here. We are working with ZK snarks, we have a prover and a verifier, and I think I nowadays take always this thinking point of view that zero knowledge is actually verifiable computation. So prover knows a computation, statement and the witness, the verifier knows computation and the public input X, and then you have a trusted third party who generates a structured reference string and sends it to both parties. And then the prover gives a proof that the computation is done correctly. So this known computation at known input and unknown W is, let's say, just equal to 1. And you have the usual requirements, completeness, soundness, or whatever, knowledge soundness, and zero knowledge. And obviously you want succinctness. Okay, so I think the kind of like one way of thinking like why I did what I did was that I was thinking about the landscape of snarks, and now there's a huge work on getting very prover efficient snarks. So there's like all kind of tensor code based stuff like breakdown, Binius. I think now the latest thing is Blaze. There's JKR with many versions. There's Fry with many optimizations, etc. And they're all good for prover. And then there's, if you look at the other side, which snarks are actually good for verifier, the list is much smaller. So I think they are mostly, I mean, up to at least in 2024 summer, they were all pairing-based. Like, I mean, Plonk was getting there, but mostly like it was really like everybody who was interested in the prover efficiency was using CROT16. And then if you wanted to get something that was good for both, then there were all kind of like tools how to do it. One of them was snark composition. So you added, basically you composed a prover efficient snark with a verifier efficient snark. And when I looked at those papers, what they were doing was like JKR plus CROT16, breakdown plus CROT16, Fry plus CROT16, there was probably a few more. There was IPA base plus CROT16, etc. But it was always CROT16. Okay. Yeah, this is going to be interesting. Maybe I should stop doing it. So, and it's very kind of surprising because there's been a huge progress in the snark land, as you all know, during the last, I think now it's more than 5 years, like 6, 7 years. There's so many amazing constructions, but there's still this CROT16 that nobody has really been able to optimize. And it's still, at this moment when I was writing this paper, it had the shortest argument, it had the fastest verifier. So, and it was really like a dinosaur, like I'm not sure, is this T-Rex or somebody? So, I mean, 2016, some people here went to the grade school at this time. I mean, not even grade school, like high school. So to give an intuition for those people who don't know what is a like snark composition, you basically have like your initial task. You have some computation that you want to prove. It's a huge computation. You have input and you have a huge witness. And then you give a proof that this computation is correctly done. You prove that x, w is in the original relation. And then the hope kind of like, here it's even good if this proof, like the output of the snark is maybe like square root of the input. Like you get like decent like downgrade, but you don't want to actually get something that is already constant size. And then the hope is that now you have a second snark that has like relatively okay prover, but doesn't have to be that fast prover because the input is like square root. But now you want this second snark to have very fast verifier. So, and the second snark basically proves that the verifier of the first snark accepted. So, because the input is long, then the first prover has to be very fast. the output of the first prover has to be short enough, but not like, you don't have to like really put your, spend like 10 years with it. And you also additionally need to have verifier circuit has to be simple because you have to prove something about this circuit. And like I already said, there's like quite a few candidates people are implementing, like the first proof could be like something like breakdown or FRI or bulletproofs or like this many candidates. I'm actually not an implementer, so I even don't know which one is the best right now. And then the second snark is that the input is going to be semi-long, so you need decent prover, but you really actually in many applications you would like to have like the as fast verifier as possible, as short proof as possible. And like I said, here people have been using CROT16 mostly. Then a few comments for those people who know CROT16. CROT16 is non-universal. The CRS depends on the computation. In this application, this is fine because the computation is that verify the computation of a given verifier of a known snark. So non-universalities, I would argue it's not an issue here. So one minus of CROT16 is already gone. Another thing is that CROT16, it has a relatively slow prover compared to all those fancy acronyms that I mentioned. But if the input is like short, like square root or something like that, maybe that's not so important anymore. But then the question is like, oh, yeah, we have this CROT16, but can we actually do something better? Here, like a very short blurb of like how Polymath, like my new construction, compares to CROT16. It's not a drop-in replacement. I personally think that actually this snark composition is maybe the most realistic application where you would like to use it. As a standalone snark, it's maybe not so interesting. So if you compare it to CROT16, so Polymath has shorter argument. This is already yay because there was nothing shorter than CROT16 for like 8 years. And shorter, here you have to like compute, like what do you mean by shorter? So I'm computing the number of bits. So if you use the standard BLS12 381 curve, then in the 128, so it's like you get 128-bit security. There maybe this improvement is not so amazing, it's like 10%. But then like as time goes on, people find more attacks on elliptic curves. So actually people gradually, I don't know, slowly move to more secure elliptic curves. Like if you remember BN 254 was a really amazing curve, but it's kind of like, it's still like used, it's still in Ethereum, etc., but it's kind of like, it's less secure than it used to be. So if you want to move to 192-bit curves, then Polymath has already twice shorter proofs than CROT16. It also has faster verifier, although this is something that I would really like to see somebody who's a very good implementer to actually give me the numbers. I was doing all the mental arithmetic here, and I found out that if the input is short, then it's potentially faster because instead of a pairing, I have a number of scalar multiplications. But then if the input is long, then it's definitely going to be faster because in the case of CROT, you do basically scalar multiplication per every input element, and here you do field operations. So, but then again, I think a lot of people use like pre-hashing, so they actually use short input, so I'm not really sure. And another thing is that it's patch-friendly in the sense that there are no adversarially generated G2 elements, and this makes certain kinds of patching much better. So if you are into that kind of stuff, it's again like, it's much better than CROT16. And the bad things are that the prover is slower. again, like I did mental arithmetic, I found out that it's like maybe 4 to 8 times lower than CROT16. So it's not maybe a very good standalone snark, but in the composition it should be fine. It uses random oracle. So that, given the discussion yesterday, this might be a problem, but I would say it's not very important maybe here, because I'm thinking about composition and the initial snarks, all those GKRs, etc., they use random oracle anyways, and I think the problem is more like with those snarks than with this polymath. But one problem is that random oracle makes certain apps difficult because CROT16 is malleable, and then you can do certain nice things like snarkback. This is not possible with polymath. So, and like what snarkback allows to do is that you can collect pre-existing proofs from several sources, and then you can patch them. And this, at least, I don't know how to do. But if you, again, this is one concrete application where CROT16 is better. So I will go briefly through the process of polymath. So the first thing is to remind what are pairings. Again, everybody here should know it. The only thing is that I'm a very strong proponent of additive notation, so I use additive notation absolutely everywhere, even in the target group. Although it's not important. I think in the next slides I don't use target group elements. So one in bracket sub 1 is element in group sub I is an element in GI, where the discrete logarithm is the stuff inside the brackets. And then we have bilinear map, and bilinear map basically gives bilinearity. What is maybe the important part in this slide is that if you are like a theoretical cryptographer, you don't think usually like how expensive is each group. But this is very relevant in practice. So you have to think that in the case of this BLS 12381, the field elements are like 256 bits, G1 is 384 bits, and G2 elements are twice longer. And if you go to 192-bit level, then the numbers blow up, and the number that really blows up is the last one. The G2 elements are 4 times longer. And then if you go to 256-bit world, then they are 8 times longer. So it's really like G2 elements are much more expensive, especially if you really care about a high level of security. So like one hint is that, what I'm doing, I'm trying to get rid of G2 elements. So very, very briefly now, so what CROT16, I'm not going to any details. What is happening is that the CRS depends on the computation, and then the proof is 3 group elements. 3 is good, but the middle one is in group 2, so it's actually twice longer than other elements, so you can think that it's actually like somehow 4 group elements. And verifier executes 3 pairings and the length of X group operations. So there's an optimality result. So CROT16 has 3 elements, and then also CROT proved that at least 2 group elements are needed, and one of them has to be in G2. So CROT16 has like 1 extra. And then there's a variant known that is using a different arithmetization where you can have 2 group elements. The idea is that instead of multiplication gates, you have square gates, and then the left and right inputs are the same, so you save kind of a 1 group element. The problem is that you have to use symmetric pairings, and symmetric pairings are very inefficient. So actually, if you don't care about the number of group elements, but the number of bits, this is going to be a much worse solution. But it's important to know that such a solution exists. So 3 group elements is definitely like not the minimum, but also if you think about this CROTS lower bound, first of all, it works in the standard model without random oracle. And the second thing is that it talks about the number of group elements, not about the bits. And if you maybe like mingle in group field elements, maybe you can like reduce the number of bits. And that was the very first thing that came into my mind, is that, oh, G2 elements are long, what can I do about it? I want to eliminate it. And then the kind of like hope is that you could, instead of B in group 2, you could have B in group 1, but the question is how. And then the basic idea is that CROT16 uses pairings for quadratic checks. And what I'm doing instead is that I'm thinking about it all as KZG commitments. I'm going to open the commitment as a field element, and then I'm using this field element to do quadratic checks. So that's very, very standard in like pairing-based snarks, like Plonk, etc. They do it always. And the nice thing is that KZG opening is shorter than a G2 element. So by opening, I mean a field element and a proof. Like field element and a G1 element, they are together shorter than a G2 element. So here is already a win. The problem is that it's still like this original B has to be also given as part of the argument. So it's still there. And in the 128-bit level, this is not a win. Interestingly enough, in the 192-bit level, this is already kind of enough, because G2 elements are just 4 times longer. So in some sense, at that level, you could stop here. And then the next step is using this same square arithmetization, where you have squares instead of multiplications. So in this case, B sub 1 is equal to A sub 1, so you don't have to transfer P sub 1, so you get 1 element less. The cost is that this makes prover roughly twice slower, because multiplication can be implemented by using 2 squarings and 1 or 2 additions, and this just blows up the circuit size. So this is, like I said, prover is 4 to 8 times slower. Factor 2 comes actually just from this, from using SAP as a different arithmetization. So multiplication gates go to squaring gates, circuit is going to be roughly twice longer. And then there's a number of very technical problems to solve. One of them is, this all sounds very nice, but if you actually know CROT16 has 5 trapdoors, and KZG has only 1. KZG is a univariate polynomial commitment scheme. So the next question is, what can I do about it? And I'm basically reducing the number of trapdoors. So the first, univariatization from 5 trapdoors down to 1. And the idea is to replace each trapdoor with x to the power of I, where x is a single trapdoor, and I is somehow well-chosen exponent that gives us efficiency and security at the same time. So this is something that I did in the BKC22 paper. I used exhaustive search for original CROT16, or a slight variant of CROT16, trying to replace the trapdoors with the powers of a single trapdoor. But the problem was that even after exhaustive search, the exponents are quite large. And like if you look at the KZG prover speed depends on the largest exponent that you can have. And you don't want to like multiply this with a factor of 20 or something. So I had to do something different. So the thing that I did was I basically used the same trick, but I first reduced the number of trapdoors. And then, because there's less trapdoors, there's a smaller system to solve to get security, and then I get smaller exponents. So first observation is that if you do CROT16 for SIP already, you have 1 less trapdoor, because there was like 1 trapdoor was related to the left inputs and another one to right inputs. So that gives me already like -1. And another observation is, well, it's not observation, it's novel work. So I noticed that the second trapdoor is needed in CROT16 to mask the CRS elements that only relate to the public input. So it's like, that's kind of like weird, like why do you need it? Because public input is so short. So here I optimize this away, and like I said, I'm using field operations here. And yeah, and an additional benefit here is that verifier becomes faster, because instead of the length of X group operations, it has to do length of X field operations. And then now we only have 3 trapdoors. We can basically, I applied exhaustive search to find out those powers of this single trapdoor that give a system where it still like has soundness or knowledge soundness, and so some elements cannot collide. But on the other hand, I want to have like as small exponents as possible, so that the KZG prover would be efficient. And the exhaustive search gave me like concrete numbers, like one exponent is 3, another one is -5, but like the rest of the slowdown comes from this fact that those exponents are not 1 or 2, they are a bit larger. The problem is that if they are going to be like 1 or 2, then there are, in this knowledge soundness proof, there's going to be collisions between the powers of X that shouldn't collide, and then the soundness goes away. And then there's another trick, so I don't, like this is very short, so it's, the problem is that to do all this stuff, I have to use like this CROT-16 setting that you have a circuit-dependent SRS, but this SRS has holes. You cannot use this SRS to compute KZG proof. So I just added more elements to the SRS that depend on a new trapdoor. There might be a more clever way of doing it, but it just worked. It almost had added no like costs. And that is the kind of idea like behind polymath. Like I already talked about the efficiency. I'm not going to give concrete numbers. They are all in the paper. I think for real efficiency, you really need an implementation. I know that there is an implementation around, but I was just recently informed by a third party that this implementation is not good. So like it's extremely unoptimized. And the very final thing that I want to mention is security proofs. One thing is that completeness and zero knowledge proofs are short and standard. There's no problem there. Soundness proof itself is 7 pages. Like if you know CROT-16, the soundness proof is very long. And now because of those colliding powers of X, etc., it gets even worse. And then I also tried to get like a bit better security. So to get tight security after Fiat Shamir, I proved special soundness. That added like half a page at least. And finally, the proof is given in the AGM with oblivious sampling. Like if you, in the TCC paper in 2023, we noted that KZG is often used strongly. Like if you look at some of the existing proofs, the proofs don't work if adversary can obliviously sample group elements. So I try to basically iron tight my proof as much as possible, but it's complicated. And yeah, I think that's it. It's first improvement on CROT-16 since 2016. I wrote that hopefully encourages other researchers to improve CROT-16 even further. I know that now there are other works. I think Pari is going to be presented soon here. And then I also saw some recent e-prints saying that if you just want to do designated verifier, then you can even just do one group element. So people are now finally working on it. And yeah, open problems, the prover speed is not so good, but I think in this application it's okay. And I think the theoretical question is that now we have random oracle, does CROT's lower bound actually hold? What is the shortest that we can get? I have no idea. And that's it. Thank you.
Thank you. We have a question here.
So you use the square arithmetic programs.
Yes.
What about using exactly the same approach, all the optimizations you've done, everything, but without the square? Like, of course, like the proof size would grow, but the prover would be more efficient, and maybe at some security level, you would also get something.
Yeah, I shortly mentioned it. I didn't work out the details, but the kind of idea is that if you, like the reason to use the square is that you get down, like you win one group element. And this is what allows polymath to be better, like have a shorter proof than GROT16, even in 128-bit level. But in 192-bit level, this is actually not needed. So yes, I think you can, basically, you get twice better prover when you just use the R1CS. So that's the trade-off.
Any further questions?
Hey, why do you need to do the univariatization? I mean, if you're going to need a special SRS anyway, because you need the holes, would you lose something by just staying with something closer to GROT16 with all the 5 trapdoors, or however much it is? Wouldn't it be a little more prover efficient because the powers don't go higher? Or?
That's a good question. I don't know how to do it. Like, because like if at least the obvious multivariate extensions of KZG have worse proof size.
Oh, you're saying the thing you need to open, if you stay with the original trapdoors, it's not just in powers of X. It's, yeah.
So
okay.
yeah, so there's going to be KZG opening. I'm using standard KZG there. So the opening is one field element, proof is one group element. I don't know, maybe there's a clever way of somehow doing it differently, but all the multivariate and even bivariate variants of KZG have a much longer proof size.
We have a question. What time for one small question, more question? All right. Let's thank the speaker again. Thank you, Elliot. And we're going to set up. Just a small reminder that after this talk, we finish the morning session, and then we have a break with some coffee and treats. Can you bring it there?
Okay,
thank you. There you go, yeah. And you can screw it a bit. Oh. There you go. So we're going to hear from Jan Bobolt.
Microphone also works. Okay. Okay, good. Cool. Hi. My name is Jan Bobolts. I'm going to talk about how to prove that GROT16 is universally composable. This is from our TCC paper that we wrote with Puya Fashim, Markus Kohlweis, and Akira Takahashi, and myself. So what is when we say we want universal composability, what do we actually mean? In UC, we express the security of non-interactive zero-knowledge proofs as follows. We have a real world, we have an ideal world, and we have an environment that's the same in both worlds, and the environment is trying to distinguish these two worlds. So what's happening is in the real world, the environment talks to a real prover, talks to a verifier, and to some sort of adversary. And then all of these have access to a CRS because we're interested in GROT16. In the ideal world, we have an ideal functionality that kind of tries to express the ideal version of a non-interactive zero-knowledge proof. So this is supposed to be like secure by definition. And then in the ideal world, we also have an ideal world adversary, which is the UC simulator. Yeah. And then in its head, the UC simulator can basically run the CRS from the real world. So the CRS vanishes from the real world and gets to the ideal world, which the UC simulator can run in its head. Okay, so what happens if the environment instructs some party in the real world to create a proof? That party would just run the Grot16 algorithm and return the proof. In the ideal world, we need to express what it means to like ideally compute a proof, and this ideal way is just to simulate the proof without the witness, giving us that all of the proofs generated in the ideal world are independent of the witness. If the environment tells us to verify a proof in the real world, that would just run the Grot16 verifier. In the ideal world, we are basically taking this proof, asking the UC simulator to extract, and say, okay, this proof can only be valid if this has been extracted correctly, so if there is a valid witness behind this, or if it has previously been output by proof. Of course, we're interested in, okay, and then the whole point of this is the environment is not supposed to be able to tell whether it's like talking to the real world with the real Grot16 protocol or to the ideal world where everything is simulated and extracted. Of course, we're interested in Grot16, so we can never reach that level of security. We don't have like strong simulation extractability, but we can do weak simulation extractability, meaning that we allow the simulator to say, hey, I'm recognizing this as a basically re-randomized version of a proof that I've already simulated. And if it says that, and it actually, this proof has been simulated before, then we don't force it to give us a witness. Okay, so this is what we're going to prove, that these two worlds are indistinguishable for a suitable version of the UC simulator. How does this work? Well, simulation is rather simple. We just use the CRS trapdoor. Remember, the UC simulator just runs the CRS in its head, so it can set it up so that it knows the trapdoor, so that's easy. Extracting proofs will be difficult, and this is what this talk is essentially about. So if we want to extract from Grot16, what are kind of our choices? We can take one of the first three strategies. So we can do a proof in the generic group model, algebraic group model, or under knowledge assumptions. The nice thing about this is we know how to prove Grot16 secure in these settings. The not so nice thing is that we don't really have good models for making these things work universally composable. So there are some models in UC that model, like, for example, the AGM and knowledge assumptions, but they turn out not to be suitable for non-detective zero-knowledge proofs. And they also point out a bunch of inherent restrictions that the AGM has when it comes to composition, even outside of UC. We could do another way, which is what people usually or often do if they want UC security, which is they say, okay, let's do encrypt, then proof. So we are doing extraction with the CRS by just decrypting. And then we can basically run a compiler that will give us a proof system that's based on Grot16, but does this additional overhead stuff. This is good because we can model this in UC nicely, but I mean, it comes with overhead. It's not Grot16 anymore, it's Grot16 plus more overhead. We also have a similar thing with the random oracle model in like a Fischlin kind of style extraction, which we also know how to model in UC, but again, it's overhead. The prover is less efficient, the verifier is less efficient. We could do rewinding, but this checks none of the boxes. So. And as usual, if you have as usual, if someone tells you, gives you such a table, you should expect that our goal is to make one of these rows just green check marks. And what we are going to do is to make the first row work. So we want to use the generic group model. And what we'll have to do for this is to make the generic group model work in UC. Okay, so let's take a look at what this would look like. Basically start with a naive version of this. So we can model the generic group as an ideal functionality, and a UC ideal functionality, which is rather simple. It would basically remember this like encoding function tau, which would send group elements to some random encoding. We have some generator, and then because all of the group elements are randomly encoded, the parties can't actually do group operations themselves. Instead, we give them access to this oracle, the operation oracle, which takes 2 randomly encoded group elements, decodes them, does the group operation, additive in this case, and then encodes the result again. Okay? So this is a way of writing down the generic group model. And then what we could do is just, okay, let's treat the generic group just like the CRS. So we say, okay, in the real world, these parties also have access to this generic group, in addition to the CRS. And then in the ideal world, this simulator basically gets to take over the generic group. This would work, in particular, when it comes to extraction, when the UC simulator is asked to extract such a Grotz-16 proof, what it can do is just like look at all of the group operations that the prover or the environment or anyone has done that led to these group elements, and basically then analyze, okay, like this is how this group element was computed. So these are kind of the coefficients of the CRS elements, Ui, Vi, and then these elements are essentially our witness. So this is how the simulator could extract in this setting. The downside, why this paper exists in the first place, is that if we follow this modeling, then similar to a CRS, we would expect that every single protocol would use an independent CRS, or in this case, an independent generic group. So basically, we only have a proof in the setting where every protocol uses a different group, which is, of course, not what's happening at all. Everyone uses the same 2 or 3 groups in practice. So this kind of proof is kind of not that meaningful. Okay, so what do we do about it? We are going to basically come up with a better model in UC for the generic group. We will call this the Global Observable Generic Group Functionality, GOGG. And the idea will be that this functionality will be global, meaning that it will be shared by many different protocols. How is this modeled? This would mean, so this is basically the old picture. If we want to say that this generic group is used by many different protocols as well as our own protocol, there's an easy way to model this in UC, because we already have an entity that represents all of the other protocols, and that's the environment. So what we can just do is say, okay, the environment also has access to this generic group. As a consequence of this, the UC simulator, as a consequence of this, the generic group doesn't vanish in the ideal world into the UC simulator, but it's now like, it's an additional thing that's still there. If you think about it, this makes a lot of sense, that the UC simulator doesn't just get to completely take over simulation of the generic group, because like imagine that we have 2 different protocols, both of them are like non-detective zero-knowledge proofs, and both of them, the extractor needs to completely take over the generic group in order to extract. That would not work. We couldn't put these 2 protocols into the same scenario or into the same composition and still claim security, because either this one is secure or this other one is secure, but we can't give both of them total control over the generic group. Okay. But we can write this down, we can model this. So this is the global generic group model, essentially. Now the question is, what happens if we do this? We just take the functionality that I showed you and run the ideal world. Now the question is, how can the UC simulator extract? And the answer is it can't. So the problem is that it used to be that the UC simulator just looked at all of the group operations that happened, but now the UC simulator doesn't get to see all of them because the environment can just do queries without the UC simulator seeing it. So the issue is that there's a very simple attack against this, where the environment just computes an honest Grotz-16 proof and gives it to the NISIC functionality. That thing would ask the UC simulator to extract. UC simulator would have no clue how these group elements were computed, so hence no information about the witness, hence no chance to extract. So we need to fix this. One way to fix it is to say, okay, obviously there needs to be some mechanism by which the simulator can actually see group operations. So let's add this just to the functionality. So this is the fully observable global generic group, which is the same as before. You can still do all of the group operations as before, but there's now this public observation list, which allows basically everyone to read. And whenever a group operation is happening, we just remember in this observation list that this group operation has happened. Okay. So the good news is that the UC simulator can extract in this scenario, because it can just, when the environment does this attack that I just mentioned, it computes the proof. It didn't see these operations, but it can look at the observation list and then see, this is what the environment did. And then do the standard extraction stuff. The bad news in this part is this is obviously, maybe not obviously, but it's way too strong. We don't get any zero knowledge anymore. Because what the environment can also do is just look at this observation list and check. The environment could ask, hey, please give me a proof. And then could check in the observation list, okay, how has this proof been computed? Has it been computed? Does it look like it has been computed using a witness, or does it look like it has been computed using the trapdoor? And these things will look widely differently in the observation list, in the trace. So basically, this model is good for observation. It's good for extraction. It's not great for ZK. If you like, you can also think of it as, the environment is sort of also able to extract the proofs. Like everyone's able to extract the proofs because everyone has access to the observation list. So we can't have zero knowledge. Okay, so if we summarize these, we have design challenges which look as follows. In a way, the simulator needs to see all of the group operations, otherwise we don't get extractability. The environment should not be able to see the operations that the simulator makes, because otherwise it can distinguish our zero knowledge. At first glance, probably difficult. But if you look closer, there's a way to make this work. And we basically use a similar solution to what has been done for global random oracles, which is we have some sort of partial observability. And we will do some domain separation between different protocols running on the same group. What this looks like specifically is, this is the whole idea of this. Basically also the main idea of this paper, is that every different protocol session, if I have multiple protocols, they all run in different sessions, and UC assigns them session IDs, S. And I will basically say that every protocol session will get a different random generator of the group. That's going to be the domain separation. And then I'm going to say that, okay, what you're supposed to do is just do operations that are based on your generator. Okay, so that's the first bullet point. These are the legal operations, and those will be not observable. As long as you keep to your generator, you're good. These will not be seen by anyone. And then there are also illegal operations, which is if you are in a different session, if you are in one session and you're using the generators of a different session, then these will be, all of these group operations that kind of pertain to foreign generators will be observable. Just very roughly, this will give us that there's a way for the simulator to evade observation by just being good and only working on its own generators. And still, some stuff is observable, so there's a chance for the simulator to actually extract at the end, which we'll see in a bit more detail. One caveat is we don't see all of the group operations anymore. The environment is definitely able to do some group operations that we don't see, but it will turn out that we see enough, kind of. Okay, so in a bit more detail, this is the new functionality. We still have the observation list. Well, it's heavily simplified, but this is roughly the idea of the functionality. We still have the observation list, and now whenever some group operation happens, we check whether this is like a legal group operation. And if it's illegal, meaning that G1 or G2 contains some foreign generator, or it's based on some foreign generator, then this operation will be added to the observation list, which everyone can see. So what does this mean? So in this setup, the simulator runs in session S star, which is our target session, and it represents this protocol. And the trick is basically the environment plays the role of all other protocols. So it's allowed to query the generic group, but only in other sessions, in different sessions, S prime. So we play this through. The UC simulator can do simulations unobserved. So what does it have to do for simulation? The idea is it takes all of the CRS elements and then the trapdoors and then combines them kind of correctly into a proof. All of these can be done on the CRS elements, and all these CRS elements, because we've computed them this way, live in the same generator. So they live in the correct session. So by this rule, none of these operations that the simulator does for simulation are observable. So the environment cannot tell whether we've honestly computed it or whether we have simulated it, because the generic group doesn't give any information about it. The UC simulator also has a chance to extract. So one way to look at this, if you take the stupid attack that I mentioned, where the environment just honestly computes a GROT16 proof, the environment cannot do this in the target session. So at some point, if the environment wants to create a GROT16 proof on our generator, on the generator that is group generator that is assigned to our session, the environment needs to do it from some different session. And basically, this will mean that these operations will be illegal. And this means that they will be added to the observation list. So when the simulator is eventually asked to extract, it will not see all of the group operations that led to this group element. But as soon as there's at least like one part of this group element that is like that's the generator for the group that's interesting. Oh, sorry, that's the generator for the session that is interesting. Then it gets to see all of those. Okay, so this was highly simplified. In the paper, we explain what it actually means for group element G to contain some foreign generator. Basically, we do some bookkeeping with polynomials. So every generator gets a polynomial and a polynomial variable. And then we keep track of what the group operations are, and then we just look at the polynomial representation of this group element to see whether or not a certain generator is in there or not. We also have multiple generators per session, so it's not the simple scenario that I just said, that there's just one generator. We also built in oblivious sampling into the GGM, which I agree should be definitely there. And then obviously these are all pairing groups, which I didn't talk about. But yeah, this is an easy addition too. Okay, so overall our result is that pi GROT16, which is basically just GROT16 in a way that it uses a random generator for the group, which I think might be normal depending on how you think about it, and then use the generic group for operations. And that UC realizes the weak NISIC functionality in the FCRS hybrid model in the presence of GOGG, which is this generic group functionality that I just showed. This in the presence of GOGG means that we are using the UCGS framework, UC with global subroutines, in order to model like global shared functionalities. So in the end, this is essentially in plain UC, but the UCGS theorem gives us a way to still argue about global stuff. We also have some concrete bounds for how many group operations actually, like what is the loss in security. Yeah, so this is essentially what's happening in the security proof for GROT16 is for extraction. Our challenge is sort of that the only things that I can observe are everything that pertains to my session's generators. So I'm missing some of the picture. But it turns out that even if your Grid16 proof somehow uses foreign generators, or there are some foreign generators in it, that doesn't mess up extraction. So there's a careful argument to be made there. On a more intuitive but wrong level, you could say that Grid16 proofs cannot contain foreign generators because that would just mess up the verification equation, which is, let's say, close to true. And then for simulation, the challenge is that there's some observability. We must make sure that the environment doesn't see that we've been simulating instead of proving. But this part is easy because the simulator, we just define the simulator such that it only operates on the legal CRS elements. Okay, so as a consequence of all of this, the take-home message, I think, is that Grid16 as is, so without any compilers, without overhead, is UC secure, at least in this generic group global model. So you don't have to have a bad conscience of not using these compilers. You can still work with stuff. This generic group idea should also enable, this is a conjecture for now, but we are thinking about this, should also enable similar extraction strategies, for example, for KZG and then IOPs. Some parts of standard Schnorr proofs, those should all be UC secure in sort of this model. It comes with some restrictions. So first of all, if you do a GGM proof, generic group model proof, then group operations are kind of only doable with the queries to the generic group model. So there's no circuit to evaluate these, so you cannot prove something about the group that the Grid16 proof lives in. So recursive proofs would become difficult, but those are always difficult for provable security anyway. And then we added this partial observability. Turns out some protocols actually can't really work, even with this partial observability. They become kind of insecure as soon as you have that. We have a workaround for that in the paper that kind of gives a different sketch of a composition theorem that gets rid of this. And that's it. Thank you.
Thank you very much. Do we have any questions? Opa.
Maybe a stupid question, but can you just bypass this completely by just using Groth16 as a verifier of in the VC sense, of a zero-knowledge, other technology zero-knowledge proof?
Bypass it in?
Bypass your complexity your complexity is because you're trying to use the zero-knowledge property of Groth16. But how about just forget the zero-knowledge thing? And just go, I'm only going to use it to VC a verifier of another zero-knowledge system. And can that composition be proved UC? I don't know.
Yeah, I would assume so. Really the challenge here is to make it work in the, it gets more interesting as soon as you have generic groups. You want to have something where some stuff must not be observable and some stuff must be observable. If you, like in your scenario, you can just make everything observable and everything just works. That's true. That would shortcut it, yes. But then you also don't get zero knowledge, which, I get the point, yeah.
So since you're using different generators for different sessions, is it correct that the SRS also has to be different for every sessions?
Yes.
So do you think there's any hope of reusing the same? So imagine different sessions actually are trying to prove the same statements, the same circuits. Is there any hope of reusing the same SRS?
Not that I have any hope, no. So the issue is that sharing CRSs is always a difficult thing in UC. We have like some results, like impossibility results for global CRSs. And I guess these would extend to this scenario as well. Maybe there's some idea that I don't see yet, but so far we don't have any idea how we would even approach this.
Hi. Can you elaborate more on like the last point on your restriction? Like what protocol cannot deal with the partial observability and why?
So the simple example is allgemein encryption. So let's pretend at some point I need to decrypt some ciphertext that the adversary gives to me. If I can't make sure that the ciphertext actually lives in my session, then I will do group operation. I don't know this. So I'm doing the group operations, I'm applying my secret key to it. But all of these group operations would become observable because I'm doing group operations on kind of illegal group elements. So the issue you run into is that you leak your secret key, which then you lose any hope of security. Now, Algamal by itself is not UC secure in any meaningful sense anyway. You can fix this by saying, okay, if you give me a ciphertext, you need to also prove that the ciphertext is based on the correct basis and everything. Then you can repair this. But yeah, you need to be careful, I think is the message. Yeah.
Any last question? No? Let's thank the speaker once again. Thank you. I remind you all we have now a break, coffee break. You'll see right here outside, and we'll be back at 11:30. Grazie toda. Welcome back, everyone. Please take a seat. You ready? Yeah. Okay, cool. I think you have here. You want to check that it works?
Yeah, sure. Should work, yeah?
Yeah. Please, John, get everybody to come in if they're in the door. Thank you, everyone. Hope you all enjoyed those delicious treats out there. The coffee was also pretty good. And Nigel doesn't seem to concord. Well, I don't know. Not every hotel conference experience had a decent coffee. All right, so we're just going to get started right on time. You have reminding the speakers that it's 25 minutes plus a few minutes questions. So please, Yannick.
Okay, thank you. Hello, everyone. So the topic of this talk will be blind ZK snarks. Is it okay to go? Yeah, okay. Blind ZK snarks. They are a cryptographic primitive that you get from combining ZK snarks with fully homomorphic encryption or homomorphic encryption. And I will also be talking about two applications, which is private proof delegation and verifiable computation over encrypted data. So I'll start by introducing the second setting and to give an introduction into this research domain. So, okay, it works. So the setting is you have a client and a server. The client has a low amount of computational resources, and he's outsourcing some computation to a server. There's an input U, there might be a server input W, is computing a function f and returning the output, right? So here you can say, what if the server is dishonest? And we can try to remove this trust assumption using something you're all very familiar with ZK proofs. So you force the server to actually provide you with a proof that the client can verify, right? But one thing you don't have here is that the server can be curious about this input U and the output, and this might leak some privacy. So there might be another cryptographic primitive we can use to prevent this, right? So yeah, in general, we call this verifiable computation, right? Okay, so quick intermezzo. I think most of you are familiar. So you have homomorphic encryption, just a normal encryption scheme, except that it's homomorphic for addition, for multiplication. We don't actually require it to be fully homomorphic here for this application, but I might just use the term FHE interchangeably. So in general, homomorphic encryption can transform some arithmetic circuit, for example, this computation F, into an homomorphic circuit, which I'll denote by eval F. And it has this correctness property, meaning that if you choose the ciphertext space parameters large enough compared to your computation, then you have this homomorphic property. And yeah, for this talk, the FHE scheme can just be symmetric, so encryption and decryption is using the secret key. So using FHE, we can remove another trust assumption. So the client instead sends a ciphertext of its input, and then the server homomorphically evaluates the function, or blindly evaluates the function, and then returns a ciphertext of the output, which the client can decrypt. But here you don't have this integrity, right? So we'll refer to this as computation over encrypted data. A natural question is, can we have both these properties at the same time and be secure against a dishonest and a curious server, right? So is it possible to send over a ciphertext, have the server homomorphically evaluate the function, but then also provide a proof which the user can verify? And we will refer to this as verifiable computation over encrypted data, or VCOED. And this is a concept that was already introduced by Fiore, Gennaro, and Pastro in 2014. And you can kind of regard it as a cryptographic variant of a trusted execution environment. But you don't have to trust the hardware, right? But as you know, zero-knowledge proofs and FHE are themselves already kind of fairly expensive protocols, so combining them is not necessarily very efficient, but we'll try to make it as efficient as possible. So let's get to the first straightforward way of achieving vCoed is by using verifiable FHE. And in verifiable FHE, you simply take this FHE scheme and you wrap a snark or some verifiable computation around it. So you take your function f, you construct a homomorphic circuit, and then you represent that homomorphic circuit in a constraint system that you prove to the client. This is verifiable FHE. But yeah, as you can imagine, this is not very efficient, right? So in the first step, you already have a circuit size blowup because in FHE, you compute these field operations in a large polynomial ring, which you'll have to represent in the constraint system. Secondly, it's not only these ring operations, right? So in FHE, you have noise, and sometimes you have to do maintenance computations to remove this noise or maintain the compactness of the ciphertext. So these maintenance operations have to be performed fairly often, and depending on the FHE scheme, they will either require some rounding or taking a remainder. And in the context of ZK snarks, this will translate into doing a lot of range proofs, mostly, on these very big polynomial rings. And you know that this is not very efficient, right? So state-of-the-art schemes will either have this function f be very small, like hundreds of operations, or do this for smaller FHE schemes that have a small plaintext space. So we can take a look at the opposite approach, right? Because in this previous approach, we are proving the ciphertext space operations, and this is more than we actually want to do. We want to verify the plaintext space operations. Right? In some applications, you do actually want to prove ciphertext space operations, and then you really need to use VFHE. But for achieving vCoed, VFHE is kind of overkill. So in 2024 at Crypto, Sanjam Garg and his co-authors proposed this opposite approach, which is to wrap the FHE scheme around the snark. So you take this computation f, you make an arithmetic circuit that represents this proving computation for proving that function, and then you evaluate the proving computation homomorphically. And we call this blind ZK snarks because essentially someone is blindly proving a computation. He knows what the computation is, but he doesn't know on what inputs he is proving the computation. And this only proves the plaintext space operations. So take, for example, when f is simply adding the input u and w, then you could compute this in FHE as simply addition of the ciphertext, but of course you can add as many ciphertexts of 0 to this as you want. In VFHE, you will notice this, right? Because you're proving the ciphertext space operations, but in blind ZK snarks, you can't tell the difference because you're proving plaintext space operations. So it's important to distinguish these two. Okay, so how do we use blind ZK snarks for achieving this vCoed? You have the normal verifier prover setting, but then the client encrypts his input, sends the input to the server homomorphically evaluates the proving operation on ciphertext, and then sends back an encryption of the output and the proof, which will also be encrypted, of course, right? So then the client can decrypt the output, can decrypt the proof, and then verify this proof. Because the proof is encrypted, this scheme is, of course, designated verifier. Only the person that knows the secret key can actually verify the proof. But as I showed in the first slide, blind ZK snarks have another application, which is private proof delegation. So let's say that the client is actually the prover. As you all know, proving computation can be fairly expensive and might be too expensive for constrained devices. Think, for example, of schemes like ZK email, ZK P2P, private cryptocurrencies. Blind ZK snarks can also help here with private proof delegation, but to a single party. Right? So the client encrypts his private input, or maybe even the entire computation trace, and then sends that to a server who homomorphically evaluates the proof, sends back the encrypted ciphertext and output, and then the client can decrypt the proof and decrypt the output. But of course, the scheme was designated verifier, so to actually be useful for private proof delegation, we'll have to make this publicly verifiable. And we show that you can do this by appending a proof of decryption, and you'll see later why. So as a summary, blind ZK snarks, you can achieve vCoed, private proof delegation, and this vCoed application kind of overlaps with VFHE, but VFHE can achieve more than this and is useful in other applications. So if you're interested in VFHE, I recommend sticking around because there will be a talk about this later. Okay, so how do you make a ZK snark blind? Normal proof systems, they just prove that a statement and a witness in a relation, but here we kind of prove that some ciphertext, if you were to decrypt them, that their plaintext representation would be in the relation. And we define this new notion of plaintext knowledge soundness, meaning that an extractor that has knowledge of the secret key could extract the witness. And it's also important to notice that if you're outsourcing a computation or the proving to someone else, then that's in a normal proof. The server could add some inputs to this, and by the zero knowledge property, automatically get server privacy. Here, this is not necessarily the case because the FHE scheme might leak some information in the noise, so you might have to use an FHE scheme that has this circuit privacy property. Okay, so how do you construct this blind ZK snark? Let's start from a normal HIOP. You send some messages, you receive challenges. You're all very familiar with this. And then you can, of course, compile this into a ZK snark using BCS compilation. Right? So you make a vector commitment of the messages, which produces a root, and then you use kind of fiat shamir to generate the challenges. And then in the end, you have to open some of the elements in the vector commitment and do some verification there. So in a blind AIOP, you do something else. So you send the encrypted versions of the messages, because that's the only thing the prover knows in this case. And we show that it's sufficient to actually use these to compute the vector commitment on this ciphertext. So you could also make a blind snark by fully homomorphically evaluating these vector commitments, but that would be very inefficient. But it's actually sufficient to just commit to the ciphertext representations. So we show that these blind HIOPs, they inherit this round-by-round plaintext knowledge soundness from the HIOP, and you can still simply apply this BCS compilation with some kind of requirement on the HIOP, which is also always satisfied. So in the designated verifier setting, the client decrypts these values that are opened in the Merkle trees. He checks some identities that which just depend on the HIOP, and then, of course, naturally checks these openings and the fiat shamir. And then you can make this proof publicly verifiable by simply appending these decryptions of the plaintext, but then also providing a proof of decryption, basically that these ciphertext correspond to the plaintext you're appending to the proof, so that anyone, even without knowledge of the secret key, can verify the proof. Of course, these proof of decryptions need to be zero knowledge as well, because they cannot reveal the secret key, otherwise you would lose privacy of your witness. So we look at how to construct an efficient blind ZK snark. So we select an IOP that is fairly linear, which is compatible with the FHE scheme. And then also we need a high precision HE scheme that allows for large plaintext spaces, because the snarks are sound because of the size of the plaintext space. So we also need the FHE scheme to be to allow this. But most FHE schemes, they don't like large plain text spaces because this increases the noise growth. Then also we need to optimize the IOP to actually be as efficient as possible for specifically HE computations instead of plain text operations. And then in the end, we need to construct a proof of decryption for that specific HE scheme that we're using. So what is the computational interface here? We have the HE scheme. It works over a ciphertext space, but the plain text are simply vectors over some finite field. And it has element-wise operations, additions and multiplications, and can also perform permutations. And so for those who are not familiar, so FHE schemes allow you to have this SIMD property, so that each ciphertext represents a vector of plain text values, and you can do element-wise operations. And we try to make use of this fact to make the blind snark as efficient as possible. Now, of course, there's also noise growth, so we want to decrease or minimize the noise growth as much as possible, because this will increase the ciphertext space parameters that we need to use in the FHE scheme. So in general, this is not very good, and there's not many FHE schemes that are compatible with this. So there was another FHE scheme kind of co-designed with this paper called GBFE, and it's sort of a best of both worlds between normal BGV and BFE, which allow for very large SIMD packings, but also simultaneously allows for this high precision arithmetic without having super large noise growth. So in our example, we have this plain text space, which is an extension field of this Goldilocks prime, and the size of the vectors is 256. We found that this is optimal for our parameters. So how do we modify the HIOP to be as compatible as possible for homomorphic evaluation? This is generally a trade-off between the number of operations you have to perform, which you, of course, try to minimize, but then also the noise depth that they cause, because if there is the circuit you're evaluating is too deep, then you have to choose a large ciphertext space parameters, and everything gets less efficient, right? So as an example, take these FFTs, and so we use fractal, and you have to encode into Reed-Solomon codes, so you have to do some kind of FFTs, which is what normally is done in the plain text space. So to minimize the amount of operations you have to perform, you just use these standard FFT algorithms. You take an inverse and then a normal NTT. But of course, this has a large depth of the circuit. So on the other hand of the trade-off, you could see that, well, these NTT operations are just linear transformations, so we could compute them as a matrix vector product. But of course, this has a large amount of operations in general, and so again, you have bad efficiency. So you want to have a trade-off, an in-between trade-off. So one naive approach might be to take the normal NTT and then squash a few of the layers together and then compute them as a matrix vector product. But this is not very compatible with this SIMD packing that you have in the FHE scheme, right? As you may know, like in FFTs, in these butterfly algorithms, if you start from a vector, your end vector will be a bit reversed version of that. And so all the elements in our slot would have been thrown around, and it's very expensive in FHE to actually reverse this permutation. So we propose another solution, which is kind of to use a two-dimensional version of the NTT. So you represent the initial vector that you're performing the NTT on as a matrix. And as you can see, where the slots are aligned as rows, for example. And then you perform one NTT in each dimension, and one will be orthogonal to the packing, and one will be parallel to the packing. So the one parallel to the packing, there you really have to use the matrix vector products to prove that part of the NTT. But in the one orthogonal to it, it doesn't matter, because those you can just permute around easily, and there you can use the FFT. And we found that this was the best solution. So with some other modifications and choosing correct parameters, we make an example estimate. So for example, for fractal in an R1CS constraint system with 2 to the 20 constraints, we estimate or we compute exactly like the amount of operations you need to do and with what type of operations, and then what kind of noise growth they produce. And then using these numbers, we could make a micro benchmark of how long would it actually take to compute this thing using the timings of the GBFE scheme. And that turns out if fully sequentially, you can do that in 9 hours. But of course, we specifically designed all these algorithms to be very parallel. So if you could assume a parallelization factor on a very performant server of 32, then you might be able to compute this in even 20 minutes. The reason we can't fully implement this is because the GBFE scheme is not yet implemented for non-power of 2 like atomics, which we have to use to get the Goldilocks plaintext space, but that is for future work. So lastly, this proof of decryption. It's very important that the proof of decryption is very cheap, because it's used in this private proof delegation application, right? So if the client who has to then make this proof of decryptions after the server homomorphically computes the proof, if that proof of decryption would be very expensive, then it kind of defeats the purpose of delegating the proof anyway, right? So we choose this sort of based on LNP 22, these Sigma protocols, because they can be more efficient. And then I'll skip over the math here. And then because we have to prove this bound on a linear operation for the decryption of the FHE scheme, we have to translate that into vector operations to be compatible with the proof. Also, these lattice-based Sigma protocols, they need special moduli so that you actually have a large enough invertible challenge space. So we have to mod switch down to this modulus at the end of the FHE operations. And then, of course, because we can only prove L2 norms, we'll have a slight relaxation factor, and this will just translate into an amount of bits, in this case 31 bits, you need to leave free of noise room at the end, which increases the ciphertext size, of course, that you have to commit to. So if you implement this with naive batching, because of course we have to provide a proof of decryption of many values, of many openings in Fry, you see the performance is like this. So for one proof of decryption, it's fairly efficient, but it scales very badly when it's increased. So we introduce a new protocol for batching many proofs of decryption by standard zero-knowledge trick, which is just to take linear combinations, and then by the homomorphic property of the FHE scheme, well, you can make use of that to only do one proof of decryption. Hey, yeah, I need to wrap up here. And this, of course, has a cost of some additional bits of noise. But then it's important, then you can actually, the entire proof of decryption will only take approximately this linear combination, and then also one proof of decryption, which results in only less than 2 seconds in one thread and 1 second for 8 threads, and the proof size is fairly small and definitely negligible with respect to all the ciphertext you have to share anyway. We implemented this in C and it's built on this new laser library. So thank you. These are some references, and then I think we still have enough time for some questions.
Thank you very much. Right on time. We have some time for questions.
So if you think of the proof as authentication, you're authenticating, so your VFHE was encrypt and MAC, because the MAC, the authentication is on the ciphertext, whereas this is, you've encrypted the MAC, so this is like MAC then encrypt, in some sense.
I see the analogy, yeah.
Yeah, okay, so there's a vague analogy there. So usually we say one is better than the other, And so, are there any kind of like separations attacks, or if you kind of take that analogy better?
Yeah, that's important to realize. So VFHE is a stronger security notion, of course. You can use VFHE to achieve these CCA-like security notions, but for simply this application, where there's just one round of interaction, you can always resample your secret key, right? So you want to encrypt your inputs, so you just sample the secret key, send over some ciphertext, and then you never have to use that secret key. Again, in these situations, blind snarks are sufficient, and they might be usable because their performance is a lot better than VFHE, of course.
Any other questions? I have one small one. To what extent can you achieve some form of like function privacy?
This is not really, especially this instantiation, not compatible with function privacy, especially because the snark we are using is pre-processing, of course. But yeah, in general, this might be for future work. I don't know how compatible it is. Yeah.
Thank you. Let's thank the speaker one more time. We're going to hear from Stefanos now. Wait 1 second. This is the thing.
Okay.
Can you bring the rest to the...
Yeah, sure.
So just wait for me to turn it to the next video.
So it seems like we don't have enough to talk about only in the context of zero knowledge, that we need to add all kinds of signatures and FHE and stuff, how it combines with zero knowledge. That was a joke, by the way. All right, are you plugged?
Hello, hello? Yeah, okay. Hello, I'm Stefanos. I'm a PhD student at Imperial College London, and I'm also a security researcher at ZK Security. And today I'm going to present a joint work with Dennis from Input Output, and Ben, who is my advisor at Imperial, and he's also working at Eclipse Lab. So this talk is going to be a bit different than the rest of the talks, because we take as granted that ZKPs that we are using are secure. The circuits we have written are secure, everything works fine, the trusted setup, if we needed one, is safe. And the question we want to address is what else we need to do so we can utilize the nice properties that zero-knowledge proofs give us, and we're going to focus in blockchain rollups. So why do we need blockchain rollups? Basically, to scale blockchains. There is an intuition of a scalability trilemma. Maybe it's outdated, maybe there are better L1s that can solve scalability, but for blockchains like Ethereum, what we do is we build layer 2 blockchains that are basically completely independent blockchains that perform all the computation off-chain, meaning in the layer 2, and they claim that they inherit security by publishing data on an L1 and verify the correctness of the execution of L2 transactions in the L1. So at a glance, what happens in a rollup is that we gather a lot of transactions in the layer 2, we create a rollup block, and then we batch together a number of rollup blocks in a rollup batch that we are going to post in our main blockchain, in this case Ethereum, and there we will have our data availability in Ethereum, and we will also verify the correctness of the execution of the L2 transactions in the layer 1 blockchain. So what a ZK rollup does is that it performs the execution, meaning the processing of L2 transactions off-chain, basically, and verify them on the L1. It uses zero-knowledge proof, or let's call them validity proofs, because they don't use the ZK property, which are basically cryptographic proofs that assure the correctness of L2 state transitions. The benefit of using cryptographic proofs rather than more optimistic approaches like fraud proofs is that you have faster finality, because the moment you verify your proof in the L1 and that L1 block gets finalized, then you can say you have finality for the L2, and also you can have better compression. And the key roles that a rollup has is a sequencer, that in most rollups at the moment it's a completely centralized component that we trust blindly, that orders transactions in the L2 and bats various L2 blocks into a batch that will post in the L1. We have a prover that generates validity proofs for the that proves the correctness of our state transitions, and we also have an L1 contract that basically verifies proofs in the L1 and keeps a canonical order of finalized states of the L2 blockchain in the L1. Here is a diagram that demonstrates those three components and how a user can interact with them. You can observe that the user has two options: one to send a transaction to the L2 sequencer, and one to force its transaction to the rollup contract, and we are going to explore that concept in a bit. So, in the rollup world, we had some incidents. I would say benign incidents where, for example, in the blast rollup, there was a very quick upgrade to censor an attacker's address. And in the linear chain, there was an incident when block production stopped for a while, so they can blacklist some compromised addresses. Although those are benign cases, that's something we don't really want to happen in a blockchain, even if it is an L2 blockchain. What are the main takeaways is that L2s are completely centralized and can lead to censorship, so you are not inheriting censorship resistance from the L1. And what that means that we need a mechanism to force transactions through the L1 and also to have a way to safely perform upgrades. And the intuition for those mechanisms is that L2s should indeed inherit L1 censorship resistance, but also user funds should be as safe as they are in the L1. And to give you more intuition of what does that mean is like the main blockchain vulnerability, it's not like reentrancy, it's not like issues in consensus, etc. We have the most losses of funds due to multisigs being compromised. And an L2, it's basically a multisig in the L1. So if we don't have some more advanced mechanisms, that means that all user assets in the L2 are in risk if the multisig is compromised. So the contribution of this work is that we provide a formal model of validity-proof rollups via Alloy. We model three key mechanisms, which are first Q, that ensures a user transaction can't be censored. Safe upgradability, which means we can perform upgrades safely, and we will explain more what that means. And safe blacklisting. So in some cases, in those L2s, we might actually want to do some censorship for various reasons, but we want to still keep some basic properties for the users, and we will see how we can achieve that. Yeah, and the main goal is eventually to provide stronger guarantees to users that what they use indeed is close to L1's properties. So our security assumptions is, as I mentioned in the beginning, that validity proofs are correct and safe. And our model is that the sequencer is completely malicious, we don't trust him. The admins, meaning the multisig, can be compromised. There could be malicious users that try to DOS our systems. And we also have like one more assumption that the L1 is trusted and secure. So our goals is to provide weak liveness to users, meaning that if L2 finalizes new blocks, then user transactions will eventually be included. The second property is that upgrades should be performed with a safety mechanism, means that users have the opportunity to exit before an undesirable or malicious upgrade is enforced. And finally, we don't have retroactive censorship, which means that once forced transactions are in the queue, then we cannot blacklist them, we cannot censor them, we must process them. And we will see why that is important. So, what is alloy and why we use it? Alloy is basically a first-order relation logic that is useful to describe system states and operations. It has a SAT-based engine that finds counterexamples in a bounded state, meaning that basically it performs bounded model checking. And it's really handy for performing protocol-level logic verification. In this work, we don't actually verify source code, but we analyze the correctness of mechanisms that are used by rollups. So let's begin and describe our model. We have inputs, which basically represent transactions submitted by end users. We have blocks, which are ordered sequences of inputs. Then for commitments, a commitment is basically when the sequencer commits that it will create a proof for that batch, and the proof is the proof for that commitment. For both of these, we keep track of the state, which is the existing state of the rollup, and a diff, which is what we commit or for what we create a proof. And we also have in the L1 our contract that models basically the L2's representation on the L1. So what is the state of the L2, what commitments we have, what proofs, etc. So here is the Alloy code. Alloy basically it's a declarative language, so it's pretty easy to understand and follow. And we explain a lot in details how to use it in our paper, but also we have some source code available that I will give you a link in the end of the presentation. So we start with a very naive rollup model, which is actually kind of what most rollups are at the moment in production. And the only thing that that rollup does is it has a process function that actually enforces proof and commitment matching and basically verifies ZKPs in the L1 and progress the state of the L2 in the L1. So what are the issues? There is no first queue mechanism and there is no safe upgrades mechanism, which can lead to vulnerabilities to censorship and malicious upgrades that could basically get all user funds out of the L2. So let's start with our first, and I will say most important mechanism, which is the first queue mechanism. It's a mechanism that almost all rollups want to implement. So we have force inputs that are posted on the L1, and those inputs must be included in the next finalized block if the L2 wants to progress. So there should be, in other words, some progress in the queue if the queue is not empty and we want to create a new and finalize a new block. What we guarantee, and it's a FIFO queue, and what we want to guarantee with that is that user transactions cannot be censored. So let's see a bit more formally what kind of properties we need to define in Alloy to achieve that. So we have guaranteed processing, which basically means that if the first queue is not empty and a new state is finalized, then the head of the queue must be processed and removed from the queue. And here is an Alloy fact basically on how you can do that. And we have always, and then we say if there is something in the first queue and the next finalized state it's different than the existing finalized state, that implies that the first transaction of our queue is in the new finalized inputs, and that the first transaction in our queue, it's not the first transaction in the next state of the queue. We also have like some more properties. The first one is that the first queue should be stable, which basically means if the finalized state did not change, then the first queue did not decrease. Another one, it's kind of a symmetric property, state invariant, which means that if the first queue is not empty and did not change, then the finalized state remains unchanged. And then we have that first inputs must progress, which basically means that when the first queue progress, all elements in the queue, all inputs in the queue should progress. And we have order preservation, that we are not able to actually change the order of the inputs in the first queue, and finalization confirmation, that if an input was in the first queue and then disappears from it, it was finalized. So let's move on to our second mechanism, which is secure blacklisting. And the dilemma that here L2s might have is that they might want some optional blacklisting for compliance reasons, or because those L2s are operated by some companies and they might have some policies. But the blacklisting can actually freeze the first queue, so we cannot make progress in the L1, given the previous mechanism of first queue we described previously, that we can't change its properties. So the solution is either to allow blacklisting to be applied after or during times that the first queue is completely empty, or to require blacklisting changes to go through the first queue, or an upgradability mechanism that we will explain later. So let's move to our upgradability mechanism. And basically how that works is that you should announce the upgrade on the L1. Then you should have some timeout window that allows users to submit transactions to the first queue if they can't, for example, exit through the L2. So they should have some time that they can include their transactions in an L1 block. And then what is important is before you deploy the upgrade, you should process all first transactions in the queue. And the result of that is that we ensure that no user is actually left behind with block first transactions at upgrade time. And let's move on to two examples. I will start with the second one. So the most common approach in rollups is to just have a naive, I will call it, a time-based upgrade, where you give some time for users to exit your L2 before you perform the upgrade. The problem with that is that someone can DOS the first queue. For example, if a malicious entity wants to perform a malicious upgrade and stop accepting exiting transactions in the L2, then it can also DOS the first queue in the L1. And after the timeout happens, if we don't empty the first queue by processing all the transactions, then some users will stack in our rollup, and they will not manage to make it before the upgrade is performed. And another common mistake we identified is that if we can enable immediate blacklisting, given that we have a secure first queue mechanism, then the L2 will get stuck. So what Alloy does is that with the facts we define in Alloy, it will create counterexamples that show how the system can break. So here it's the blacklisting example. And basically, what we have here is that we start with an empty state where everything is basically empty. We have first queue, which is empty, blacklist, which is a policy for blacklisting, which is empty, and ongoing upgrade, it's none. We include an input in the first queue. So now we have an input in the first queue, the blacklist is empty, and ongoing upgrade is empty. Then we announce an upgrade policy that basically blacklists the input one, and we have a timeout that for that policy, the status currently is false, and in the next step, basically we change the status to true. And what happens in the end is that the first queue now has input one, the blacklist has input one, and remember the rules we had in the beginning of the presentation. Now we cannot make any progress. So that's how Alloy will try and find counterexamples that are pretty useful to understand what is working in our system and what not. So we basically Alloy does bounded analysis, right? So you set a limit of how many steps it can perform, and then it tries to do model checking based on that limit. The hypothesis here is that many design flaws in protocol design appear even in small examples. So you need not that many steps to find all the issues. Here are basically the numbers when scope is 5. So lines of code is independent of scope. So the simple, very basic roll-up model was written in almost 300 lines of Alloy. And then the simple model with the first queue mechanism was written in 500 lines. If we add blacklisting, is 700, and then with upgradability, it's close to 1,000 lines of Alloy code. And then we can use the solve time for scope 5. What we observe is that we can go for, like, in a laptop, we can go up to scope 9 to 10. After that, basically, Alloy will not manage to solve our model for the most complicated ones, meaning the upgradability. Okay, so what we presented is that an Alloy model that basically we can use to verify that the properties we want in a rollup actually hold, and indeed the rollup inherits some properties from the L1. What is an important takeaway is that when we use ZKPs in general, we typically integrate them in some broader system. So we must understand what the ZKPs provide. In this case, they provide validity proofs. So, and then we need to design our system to correctly use the zero knowledge proof. And because of the very strong properties the zero knowledge proof give us, we should make sure that the rest of the system also enforce what the system should do. And in that case, we did it with Alloy. So in the rollup context, what we did is we manually checked the implementations of the rollups and tried to encode everything manually to Alloy models, which might be not that practical because we don't verify the source code. So one option could be like to go from source code to Alloy. Another option could be to go from Alloy to source code, to smart contracts, basically, that enforce everything. Both options, although could be possible, require a lot of effort, and you might introduce various bugs trying to implement them. So what we actually propose is a pragmatic approach where you have a design spec written in Alloy, and from that design spec you have verify some critical properties, and then you can use those critical properties that you know are correct through bounded model checking to use them for performing formal verification or even property-based testing of the actual implementation. And something else we need to do for rollups is basically to add in all of that security councils and how those could affect our analysis. So you can find our paper in archive, and also you can find all the alloy implementation in that GitHub repo. So that was it.
Thank you very much. Do we have any questions? Any brave one?
Thank you for the presentation. And I was wondering, the competitor to ZK rollups is optimistic rollups, which introduce a lot of complexity due to handling fraud proofs. Do you think your approach would generalize to those?
So that's a very good question, and we tried to tackle that, but it turns out it becomes way more complicated because with fraud proofs, much of the logic goes actually to your smart contracts in the L1 that needs to also implement fraud proofs. So we would have to basically model the fraud proofs in Alloy, which makes it a way more difficult task to do. And the nice thing about using zero-knowledge proofs is that, okay, you can assume are secure, and then the only thing that happens in the L1 is that you verify a proof, and that's it. So it's way simpler to model a system that uses ZK rather than an optimistic approach that requires more logic.
Any other questions for our speaker? All right, let's thank the speaker again. Thank you very much, Stefanos. We're going to hear from Daniele.
So, presented the second paper on verifiable computation for homomorphic encryption for today. So this is a joint work with my co-authors, Ignacio, Ana, Dario, Antonio, and Eduardo. So let's start. I'll go through this very quickly because you already had some glimpse from the blind snap presentation. So cloud computing is can be seen as interaction between a weak client that outsources and heavy computation to a powerful server. The powerful server computes, sends the result back to the client, and that's it. But I mean, there is a problem with privacy because then the client needs to expose his own data, and we don't want this. So solution is FHE. You encrypt everything with an FHE scheme, and this grants you privacy. But I mean, you are assuming that everything is done correctly. FHE doesn't protect you from a malicious server. So what we really want is to add a layer of integrity. So that brings us to verifiable computation over encrypted data. A verifiable computation scheme is something that provides you privacy, integrity, and succinctness. Just sanity check. If you need to provide a proof that the whole process was carried out correctly, and the proof should be short so that even the weak verifier should be able to verify in an easier way than recomputing the function, the computation on the plain text. Otherwise, it doesn't really make sense. So question is, can we have both of them, verifiable computation and HE? Actually, the real question is, can we have them practically? And this is really one of those problems that theoretically can be, there is a solution there, but translating it into the real world, it's really a real hard problem. So let's see what has been done so far. So the obvious approach you might try is that you take your favorite snark and you are running it on the computation that happens on the ciphertexts. So if, I mean, your snark is publicly verifiable, so is the verifiable computation, and so also if it's, you can do this with any FHE really. Also you get succinctness from the snark, so theoretically it works. Practically there is a problem because probably your favorite snark is going to be defined over fields. And now, FHE lives in a different world where you have rings, polynomial rings, where you have composite moduli, you have very non-algebraic operations like noise maintenance operations and bootstrapping. And even worse, that sometimes you also need to change ring during the computation. So what happens is that you would end up emulating, for example, arithmetic over the ring with field operations, and you would need to prove all these non-algebraic things. That said, this results in a huge blow-up for the prover. I think there was a survey a few years ago, this one, they estimated that just for scaling you would need a circuit of 3 billion gates with a field. So what you would try to do then is to define a snark over the rings, which is what Rinocchio is for. It's basically a Pinocchio Groth 16 over rings. And then you have native arithmetic over rings, but still it's like you need to, like, again, emulate all these horrible things. Well, okay, if you really want to do anything natively, then there is the blind snark approach that you saw before, which is kind of a different direction, because now you're not proving things on ciphertext. Instead, it's like it's the prover who homomorphically computes an encrypted version of the proof, sends the proof back to the client, and it's the client that checks the proof on the plaintext. So all of these things are kind of for free. It's agnostic to noise management operations. But it has inherent problems. I mean, the fact that you need to decrypt exposes it to, well, first you cannot get full-fledged public verification because you need the secret key at some point. You can have some, as you saw before, like some mitigation for this, but you cannot get fully public verification. Also, you are exposing it to verification oracle attacks because the prover is always able to learn something by enforcing decryption errors. So it's not even semantically secure. And the last, well, importantly, it doesn't capture all homomorphic encryption schemes, because since you are relying on a proof defined over the plaintext, it means that the plaintext space of the homomorphic encryption scheme needs to have some algebraic structure, which is not the case, for example, for CKKS. And you might wonder why CKKS is such a big deal. Well, it's just because you can do, it allows you to do fixed point arithmetic and you can do this with lots of cool things like training neural networks, very large neural networks, for example. So what we try to do is we go back to the previous approach of VFHE, as it's called, And, well, we tried to design something that wasn't possible before. We tried to adapt, we tried to attack the ZKKS encryption scheme and have all of these operations kind of efficiently. Well, bootstrapping is something that we don't really cover, but our techniques should apply, hopefully. So, our contributions, we design a modular solution for verifying computations for ZKKS. And the approach we follow is given by this workflow. We start with an arithmetic circuit for homomorphic encryption. Actually, we design something called proof-friendly ZKKS, which is a version of ZKKS that is more suitable for proof systems. Then we arithmetize the circuit relations to get relations over RQ. And actually, it turns out that there are only two relations that describe ZKKS computation. And then we design polynomial IOPs that prove these relations. And then finally, we compile the polynomial IOPs with a polynomial commitment. And this is also where we introduce some improvement to breakdown. And with that, we get a verifiable computation for ZKKS. All these things, proof-friendly ZKKS, arithmetization, and custom GKR, proof system, range proofs for RQ, and improvement of breakdown are our contribution. So let's start with proof-friendly ZKKS. Let's first set up the ring. ZKKS is defined over RQ, which is the polynomials with coefficients in ZQ modulo the 2n cyclotomic polynomial. Q is around 300 bits, and n is usually 2 to the 14 to the 15. So first thing we care about is that the prover should be efficient, like should do homomorphic computations efficiently. So we want RNS. So Q is products of small primes, and our Q by CRT is isomorphic to the products of these rings. Second thing we care about is soundness. We are going to run a proof system over ciphertext. So intuitively, the proof system will have soundness that is proportional to the smallest exceptional set. An exceptional set is a subset of RQ that where the difference of any two elements is invertible in RQ. So we need to make sure we have a large enough exceptional set in RQ. And for that, we further apply the CRT, this time to the cyclotomic polynomial, and we get a further splitting. And again, by CRT, we get that RQ is isomorphic to the product of these small rings. And it turns out that these are, in turn, isomorphic to extension fields of some degree D. So the size of our exceptional set is going to be equal to the smallest of these extension fields. To get 100 bits of security, we can either choose of having primes of 32 bits or 62 bits, and we can take D equal to 4 or 2 accordingly. But it turns out that the optimal efficiency is when we get, it's for 49 bits for primes and equal to 4. So to get an idea how ZKKS works, it's like a level scheme. So you organize the computation into levels, multiplicative levels. Each level is composed by a layer, multiple independent multiplications. And you define a chain of moduli starting from Q, and then you define recursively the others by scaling down by the primes that define the RNS. So for example, in this example, you have layers, to levels. The wires in the first layer are in RQ1 or RQ, and then the outputs are in RQ2, and then after another level of multiplications, you end up in RQ3. So let's see how multiplication works specifically. A ciphertext is a pair of RQ elements. Each RQ element in RNS form is given by several slots. And here is how the message and noise are encoded in RQ. The blurred part means that, well, in CKKS you don't really have a distinction between message and noise. But let's see how it works. Suppose at level 1 you want to multiply two ciphertext A and B that are the encryptions of M1 and M2. So first thing you do is a polynomial multiplication that gives you a ciphertext with 3 slots that encrypts the product, and well, the noise grows. So next thing you want to do is first to reduce the number of slots to 2 and also reduce the noise. So first goal is accomplished by a key switching, which basically doesn't alter the noise. And then finally, you do a rescaling by P1. P1 divides everything by P1, and then you remove the last slot in RNS representation. So you see that now you are in RQ2. Second level is just the same. It's that rescaling is now by P2, and you remove another slot. So you see that the ring changes. And this is a nightmare for a proof system, because imagine like you need at some point to commit to values that are in different structures, and then you need to relate them. So the most important thing we do is that we modify the rescaling. In our CKKS, everything is almost the same, except the rescaling. When it comes to rescale by P1, well, we embed the result back to RQ. And, well, you can think of like we are adding a 0 to the slot that we are nullifying, that we are removing. So it's like we are having, at the end, an element in RQ2 inside RQ, the big RQ, just with some padded zeros. So next level is exactly the same, and we add another 0. So in our CKKS, the ring doesn't change. So you might wonder like how this is in practice, because we are, unlike CKKS, where the size gets smaller, we are always doing things with a big ring. Well, it's not a problem, because at the end, it's true that you are managing, handling big things, but you have operation with zeros, so they don't really affect performance. And well, for the comparison, you can see that you have normal CKKS, and for a normal CKKS multiplication, we are just 10% or 20% slower, which is really nothing. So in summary, what is our proof-friendly CKKS? It's a CKKS where we choose the parameters in such a way we have high soundness, and we do not sacrifice efficiency. And importantly, everything works with the same ring. We don't have to switch. And there is another contribution here that it's a bit technical, so I'm not going to talk about this. It's that we also set the parameters so that we can prove approximate bounds. So for example, if you need to prove that, you want to prove that something, a ciphertext of coefficients bounded by some b, a prime, which can be a prime, we instead prove that it's bounded by the closest power of 2. This is very good for example, for if you need to batch things. So let's see the next step, arithmetization. How do we arithmetize a CKKS circuit? So you have an arithmetic circuit for in the FHE world, and we want to translate it in terms of RQ. So let's see, I'll just show you how to do this with a multiplication. So multiplication, if you remember, it's a polynomial multiplication followed by key switching, followed by rescaling. Let's analyze each of these. Multiplication, we are lucky. It's a very algebraic operation. You can express things over with an arithmetic circuit over RQ. So I will use the green color for something that we know how to deal with this. Now, when we go further, we find the very first obstacle. You have this CRT minus 1D2, which is the very first non-algebraic operation. It's basically taking an RQ element and it's giving you, computing the CRT decomposition. So you have to do a modular reduction for all the primes of the RNAs. So this is not algebraic. How do we prove this without having us blowing up a circuit? The idea is the prover, we let the prover send us a vector which he claims to be the CRT decomposition of D2. So he needs to prove this. So he needs to prove that the components of this vector are less than all the PIs. And that, of course, they recompose to D2 when you are taking the scalar product with the base, the RNS base. Okay. So basically, once he proved this, well, we can use these inputs to continue the computation. And well, we reduce this horrible red thing with just two relations that, well, one, we know how to deal with this, and something that looks promising, a range proof. So this is pictorially what happens. The prover sends us this vector, checks that they are the correct bounds, checks that they recompose to D2, and once he proves this, we can use this to go to the next operation, which is also non-algebraic, because there is another modular reduction. Again, how do we prove this? We use, again, non-determinism. First, let's rewrite it in a way that now might look a bit more familiar. And indeed, this is just a Euclidean division by PL. PL is the prime that defines the current level. So we want to prove a Euclidean division. And again, we let the prover do the job. He's inputting values, W quotient, W reminder, so that they satisfy the obvious relations, definitions of Euclidean division. So all these two inequalities, and that they satisfy the Euclidean relation. And again, once it does it, we can just use these two things, and these are going to be the outputs. These are going to be the inputs to the next level. So at the end, this is what a multiplication CKKS looks like in terms of RQ. A bunch of arithmetic circuit relations and a bunch of range proofs. And we can merge all of this together into a unique, in a single arithmetic circuit. And we do this level by level. We connect the outputs to the inputs of the next layer. And so we are sort of flattening a circuit. We merge all of this into a unique arithmetic circuit. And now you can see that at the end we got just two relations, arithmetic circuit and range checks. So next I'm going to explain you how we prove these two relations. First is arithmetic circuit satisfiability, for which we design a custom GKR. So like GKR, we are encoding this circuit with another circuit made of layers of equations, where the first layer has the outputs and the last layer has the inputs, and we prove the consistency of those equations relying on the next layer, starting from the first down to the inputs. Now, unlike GKR, we need this thing to work over RQ, and while GKR just has two predicates for addition and multiplication, we also add more predicates to be more expressive, to deal with this with what I showed you before. And the cool thing is that with those custom gates, we are able to do everything with just 4 layers. So we got something of constant depth, which is really cool, because if you think about it, GKR might be really efficient when you have something very wide and that has short depths. Next, range checks. So now we've got a vector of RQ elements, and we need to prove that the coefficients of V have satisfy some bounds. For example, this might be one of those moduli from ZKProof. Now, this can be thought of as a lookup argument of V into this table, the m tuples with elements in 0B. But problem is this table is huge. It's really huge. We cannot even materialize it. So what we can try to do is to use some decomposition techniques, for example, lasso. So the idea is we decompose B, and we reduce the first big lookup to smaller lookups. But still, this doesn't work, because the killing factor, what really kills efficiency, is this n, the dimension of the ring. So what we really want is a decomposition for rings. That's our contribution. We extend lasso to work for rings, for polynomial rings. And if we do that, we are able to reduce the very first big lookup into smaller lookups of integers. Now, these are just normal lookups that we can attack with just normal memory checking techniques. So, final building block is the polynomial commitment. We need to commit to elements in our queue, multilinear polynomials in our queue, where our queue splits as these small fields. And the very first thing we do is we reduce the problem of multivariate polynomial commitment over our queue to these small fields. Then we can use a field agnostic multivariate PC like breakdown. And this works because breakdown also doesn't assume anything from any structure for the field. But it's legit to ask if we can actually use what we have. We have some structure. We have at least n2 roots of unity, and can we use them to gain some efficiency? And the answer is yes, but we need to modify a bit the underlying encoding scheme. So suppose you want to encode a vector of m field elements. M is usually more or less the square of the size of the proof. So usually it's way bigger than n halves. So we divide it into chunks of length tau, but tau now should be less then enhance, so that now we can use Reed-Solomon encodings for all the chunks. And the final encoding is just the composition of these encodings. Doing so, we get a 10 times percent improvement on normal breakdown for field diagnostic for general rings fields. Sorry. And just to conclude, we got the very first study to verify ZKKS computations. Our techniques really should be very easy to extend to FV or BGV. One of our main contributions is the description of the problem in a very modular ways, and we design building blocks to solve these sub-problems. In particular, the design of a proof-friendly version of ZKKS, a custom version of GKR to deal with the arithmetization of ZKKS, and range proofs for polynomial rings, and finally an improved version of breakdown for fields of medium size. And we also implemented all the building blocks, and turns out they are very efficient. Thank you, and I'm taking questions if you have.
Thank you very much for the talk. Are there any questions?
Thank you for the great talk. Do you have any performance numbers, like some results?
Not here.
some ballpark numbers?
This should appear soonish on GitHub.
Ah, okay. So you have
well, in the paper, of course, you can find all your everything you want to know about them.
Great talk. What was the very specific ZKKS thing in your construction that you said that at the end you might be able to generalize this to BGV and BFV? So what's the real ZKKS bit in your thing?
We used the RNS version of ZKKS.
Yeah, but you just seem to do mod switching and stuff like that. What have I missed?
I'm sorry?
Oh, we'll do it offline. I seem to have missed something. But anyway, yeah, well, we'll talk offline.
Last question. Okay, let's thank the speaker once more. Happy to give the mic to Dan Bonnet. Professor Dan Bonnet, please.
Okay, yeah, thank you all. All right, so this is going to be a little bit of a different talk than what you've heard this morning. It was supposed to be sort of a keynote, so I thought I'd give a slightly higher level talk. Hopefully it'll be clear, everything will be clear to everyone, and enjoyable. So let's get started. What I wanted to talk about a little bit is basically how to use lattices for folding techniques. Okay, so yeah, we'll see how this works, and this is all joint work with Bini Chen. There are 2 papers on this now, and actually there's a third one that I will talk about later. Bini, by the way, is out looking for a position, so if anybody is interested in hiring him, he's fantastic, and you should do it. All right, so with that, let's get started. So let's see. So what are we talking about? So the first thing I have to do is just well, everybody here knows what a snark is, but I do have to set terminology. So let me just remind you that a snark basically operates on a circuit. So it's a circuit, it's an arithmetic circuit over some finite field. It takes a statement and a witness. I'll typically be using pre-processing snarks. So there's a setup algorithm that will pre-process the circuit to generate the proving key and the verification key specific to the circuit. And then these are given to the prover and the verifier. And as usual, the prover is given X and the witness. The verifier is given X and the proof and decides whether the proof to believe the proof is not. Yeah, so everybody here should be familiar with this. I hope that's not new. If this is new to someone, then you're probably in the wrong room. Okay, so as usual, we want the proofs to be succinct and they need to be fast to verify. We allow the verifier to run in linear time in the size of the statement because the verifier has to at least read the statement. This is, by the way, kind of the reason why we need a verification key. The verifier doesn't have enough time to even read the circuit. Yeah, and so if it can't read the circuit, it has to have someone summarize the circuit for it, and that's the purpose of the setup algorithm. It generates a verification key that's a summary of the circuit, which is then allows the verifier to check the proof, even though the verifier can't read the circuit by itself. Okay, good. So I thought I'd start off with a few examples of things that we do with snarks that have nothing to do with blockchains. They're just kind of interesting examples, and then we'll move on to Latticefold. One thing I want to point out is kind of these examples of applications for snarks are only possible because snarks have developed so rapidly in the last couple of years, and a lot of that is only possible because of their blockchain applications. So what I want to show here is application of snarks that have nothing to do with blockchains, but those applications are only possible because of the effort that the blockchain community has put into developing good snarks. I think we don't say this enough, that really it's kind of, first of all, congratulations to all of us, to all this community in developing this amazing progress and making things like this possible. But a lot of this is also possible because there is such a strong business need for these things to develop. But let me start with the examples. So the first example we call ZKPi. This is joint work with my students, Evan Laufer and Alex Ozdemir. And the question is basically, how can we prove knowledge of a lien proof? Yeah, so specifically, in this case, the statement that we want to prove is that I have a lien proof. Lien, as you know, is a language well, it's a theorem proving language. You can state theorems in lien, and you can state proofs in lien. So X, the instance, is going to be a theorem in lien. The witness is going to be a proof of the theorem in lien, and the circuit that we're going to be using is a circuit that basically checks whether W is a valid lien proof of the statement X. So really what the circuit has to do is just implement effectively the lien verifier. So this work was basically, how do we build a ZK snark system that can encode the lien verifier? So that's exactly what ZKPi does. The cool thing about this is that no matter how long your lien proof is, the snark proof is going to be really short. Yeah, so it's like under a kilobyte. Again, no matter how complicated the proof is. So that's kind of the point. I like to say that Fermat would have loved this. You know, he didn't have enough space in his margin to write his proofs. So what he could have done is he could have used ZKPi to take his proofs, compress them to a short proof, and then write those proofs in the margin. I gave this talk to a math audience at some point, and they said, this is not possible. You can't take a long proof and compress it into a short proof. And they're right, because really what this thing actually proves, what this compressed proof actually proves is one of three things. Either the theorem is correct, or somehow you maybe, let's say, broke SHA-256, right? So it's not really proving the statement. It could be that the crypto is wrong, or you got really, really lucky. Yeah, it's like one of those three things must happen, and that's basically what these proofs do. I have to say, like one of the interesting things about this is, so Fermat could have used it, but let's be a bit more philosophical for just 1 second. It's actually very likely. So here's a bold prediction. Yeah, it's quite likely that in this century we'll have a proof of the Riemann hypothesis, but that proof will be generated by an LLM. Yeah, the proof will actually, not an LLM, but it'll be generated by a machine learning model. Yeah, the proof will be written in lien, so we're guaranteed that it's correct, but it might end up being like 1 billion pages. Yeah, so no human will ever understand the proof, even though we know it's correct, and we'll never even be able to print it out on any piece of paper. The nice thing about that is we can take that proof, stick it into ZKPi, generate a short proof that the Riemann hypothesis is correct, and at least we can print it on our shirts and say that we have a proof on our shirt that the Riemann hypothesis is correct. Or SHA-256 is broken, or we got really lucky. One of those. What's interesting about ZKPi is, so as you can see here, it can generate, so Lean, I should back up just a second. Lean has a standard library with standard axioms like the pigeonhole principle and all sorts of theorems that go into the standard library. It also has MathLib. MathLib, by the way, is a really impressive project. So MathLib is a project that tries to encode most of undergraduate math in Lean. Yeah, so it's lots of well, what can I say? It's a formalization of lots of mathematics along with formal proofs of basic theorems in these areas. So because these, so let's see. So ZKPi actually doesn't implement all of Lean 4. It implements a subset of Lean 4. As a result of this, we can actually prove, not all of these standard libraries, but a fair fraction of these of the theorems in these libraries. There's actually a lot more work to do here if anybody's interested in completing the verifier and building like a full verifier for Lean 4. Hopefully, we can kind of get all the theorems proved in snarks from these systems. So there's actually a bit more work to do here. Okay, good. Right. So that's one example that I wanted to give. For how to compress proofs, how to compress Lean proofs. The second example I wanted to give is more in the machine learning setup, which is what we call ZKProof. So ZKProof works as follows. So the goal is basically what we're starting to see in the real world. So we have, like, let's say, a bank that trains a model. This model is supposed to decide whether your mortgage application should be accepted or rejected. Yeah. So you send your financial data over. Oh, sorry. So you send your financial data over to the model. The model evaluates your financial data and then sends you a response saying, your loan application was accepted or rejected. One problem here, by the way, so when you get your response, you might be wondering, well, why did the model decide to accept my application or reject it? It turns out there's actually at least in the US, there's a regulatory requirement to provide an explanation. You can't just say yes or no. You have to say you were rejected because of this and that reason. So how do we do this in the context of machine learning? Well, maybe some of you know there's this algorithm. It's a fairly famous algorithm called LIME. Might be good for you to know regardless, that actually provides an explanation for a decision. So the way LIME works is you give the model your financial data, which is a point in Rn, so a point in Q. What LIME will do is it will build a linear model that approximates the complicated machine learning model around the point Q. Okay, so it's a local linear approximation of what the machine learning model does. And if you think about what this local approximation does, it basically shows you what are the weights that are given to different attributes of your financial data. And based on those attributes, it decides whether to accept or not. So attributes that have a high weight under this linear model mean that they had a lot of influence on the decision. Yeah, so by looking at the attributes that had high weights, you can get an explanation for why the decision was the way it was. Okay, so this is called LIME. It's actually kind of a complicated algorithm to produce these decisions. It has to kind of run the model on lots of points around Q, build a linear approximation, and that linear approximation is the explanation for why the model did what it did. Yeah, does that make sense? That once you have a linear approximation, the high weights of the linear approximation tell you which attributes were used to make the decision. So what we were wondering about is, well, you submit your data to the bank, a decision comes back, an explanation comes back, but you have no idea that they actually run the model correctly, that maybe they just made up the explanation, who knows what they actually did. So we're cryptographers, so to us every problem in the world can be solved using cryptography. So let's try to solve this problem with crypto. So what would happen here is basically the bank would commit to their model. So you can see that Alice has a commitment to the model theta. And then what this ZKProof system does is it actually provides a proof to the user. And the proof basically proves that, first of all, the commitment is really a commitment to the parameters theta of the model. It shows that the decision really is the result of applying the model to the query that Alice sent. And the important part is that, in fact, the explanation that you received is, in fact, a LIME explanation for the query Q using the parameters theta. Does that make sense? So basically, the challenge for us was how do you implement this predicate? The first two steps were actually done before. This is the classic problem now has a name. It's called ZKML, ZK in machine learning, which is how do you prove that a committed model was evaluated correctly? That's the first two steps. What's new is basically proving that LIME actually was evaluated correctly too. So that actually took some work in basically implementing LIME efficiently in ZK. But we did that it works. And I guess I threw in a graph from the paper. We looked at 3 different models that are used in financial applications. Like this is an income predictor, a loan application risk predictor, and so on and so forth. And we extended this library called Ezekiel, EZKL, to actually build these proofs. So this is just an extension of a standard library to do ZKML, and you can see that like within a minute or so, we're able to produce these proofs. Again, there's probably a lot more work to do here. We can probably do this much faster. There's probably other models to experiment with, maybe use other libraries than EZKL. But generally, this question of like how much can we prove that ML models work correctly? Not just that they work correctly, they provide the right explanation, maybe that they're fair and so on, is all open area territory for building strong ZK models. Okay, so that was just kind of my general examples of things that we can do with snarks now that we couldn't do a decade ago, which is, again, thanks to this community, thanks to the fact that snarks have improved so much. So now I'm going to switch gears. So now for something completely different. So now I'm going to switch gears, and we're going to talk about lattice fold. Yeah, so good. So the point of lattice fold is basically to provide, to look at a post-quantum snark. And so let's see what can we say about post-quantum snarks. Okay, so let's get started. So far, so good? Okay, let's do it. All right, so really, if you zoom out, we sort of have three families of snarks. Yeah, so there's snarks based on pairings. Maybe I should have written curve-based snarks, but really the best ones are based on pairings. We have hash-based snarks, and we have lattice-based snarks. Yeah, these are kind of the three families of snarks. What's interesting, whoa, this is kind of dangerous. Okay, what's interesting is that if you look at the proof sizes that they generate, they're actually quite different. Yeah, so pairing-based snarks generate relatively short proofs. The hash-based and the lattice-based systems generate much larger proofs. Verification times are also quite different. You can see, well, what can I say? So somehow lattice-based snarks, at least some of the ones that came out recently, the verifier has to do relatively more work than in the other systems. And finally, I guess the thing that's of interest to us is this question of folding, which I'll say more about in just a minute. And so when you look at folding, again, we'll talk about folding in just a minute. Folding is a way to do recursive snarks. So if we want to prove a large statement, how do we break it down into small statements and do these proofs piece by piece? One at a time, piece by piece. Folding using pairings actually turns out to be quite fast and quite simple, as we'll see in just a minute. For hash-based snarks, this is harder. There's a system called ARC, a relatively recent system that shows how to do folding for hash-based snarks. It's a bit more complicated than for pairing-based snarks, but it can be done. And the question we wanted to explore is basically how do we do folding for lattice-based systems? So the question was, is it all possible? Is it efficient? Does it work well? And what I want to show you is that even though lattices have so far maybe have had some issues with building competitive snarks, lattices are great for folding. Yeah, so if there's one takeaway from this talk is that lattices are really, really good for folding, and that's kind of what I want to show you. All right, so let's get to it. All right, so I guess I have to start at the beginning. I didn't know exactly what level I should start. So let me start at the beginning, and let's talk about IVC PCD. So I like to call these incremental verifiable computation or proof carrying data. I like to use the term piecemeal snarks for them. Really what we're doing is we're taking a very large statement that we want to prove, we break it up into small statements, and then we prove every small piece on its own. So I like to call these things piecemeal snarks. And the way this works is, if you have 1,000 transactions that you want to verify, what you would do is basically, I guess we saw these pictures earlier today. What you would do is basically you would verify the proof incrementally. You would verify the first I transactions, then that proof for the first I transactions would go into the next verification circuit. You would build a proof that the next transaction is correct, and so on and so forth. Yeah. So basically, at every step, you build a proof that all previous steps were correct, or rather that you have a proof for all previous steps along with the current transaction, and that gives you the proof for the next step. Okay, so this is kind of a standard IVC structure. I imagine everybody here is familiar with this, I hope. The problem with this is that this is a little problematic. Yeah, so on the plus side, this greatly reduces the memory footprint of the prover, because the prover is only proving relatively small statements. The other huge benefit, the reason people like to use recursion, is you can start to build the proof before the statement is fully known. If you have 1,000 transactions, you don't have to wait for all 1,000 transactions to be given to you. You can start to build the proof as the transactions come in. With a monolithic snark, where you prove the entire statement at once, you would have to wait for all 1,000 transactions to come in, and only then you can start building the proof. And also, it turns out this is highly parallelizable. Here I explain it using a line, but of course you can do this also using a tree, in which case you get nice parallelism. The problem with this approach, though, is it's kind of complicated. Yeah, so first of all, this verification circuit is not simple, and so now we have to absorb the verification circuit into our snark verifier, into the circuit we're actually proving. And the other problem is the prover has to generate a full proof at every step of the computation. Okay, so there's kind of two limitations. Yeah, complicated verification and full proving at every step of the computation. So the question is, can we do something better? And that's exactly where folding comes in. Okay, so that's a beautiful, beautiful idea of folding, which turns out we can simplify both of these steps while retaining all the benefits. So let's see. So let's start with folding schemes. So to introduce folding schemes, I have to tell you about linear homomorphic commitments. I think everybody here knows what a linear homomorphic commitment is. I'll just say, given a vector, we commit to this vector, and the homomorphism basically says that given two commitments to two vectors, it's quite easy to build a commitment to their sum. Okay, so those are linearly homomorphic commitments. It turns out, again, this ARC system that I mentioned before actually is able to do folding without linearly homomorphic commitments, but we're not going to talk about that here. Here we're going to focus on proof systems that use linear homomorphisms. Okay, so what do we do? So in folding, the first thing we have to do is we have to rewrite our statement in a way that's amenable to folding. Okay, so we're going to call this, so we're going to take our NP statement, which we call R sub NP, and we're going to rewrite it in terms of R sub com. Okay, so what is the difference? The difference is relatively simple. All we did here is we basically exposed a commitment to the witness in the statement. So you notice we expand the statement from X to X comma commitment to witness. Okay, so that's the new statement U, and the witness still stays the same. And what we're proving is that X and W are in the language, are in the relation, and that in fact CW is a commitment to W. Okay, so that's kind of the first step that we have to do in preparation for a folding scheme. Great. So the way the folding schemes work themselves, the way they work now with this R sub com, again, I think we saw this picture earlier today, but I'll go through it again just to make sure everybody remembers it. So the way folding works is basically we start with two statement witness pairs, U1, W1, and U2, W2. The folding prover will work very quickly to produce a folded statement, so U tilde and W tilde, plus a folding proof that just the folding was done correctly. Okay, so this is this little proof pi that's produced. What the verifier will do is it will take the two folded statements, it will take, the original statements U1 and U2, along with the folded statement U tilde, and the folding proof pi, and decide whether this is a correct folding or not. Okay, so that's basically what folding, syntactically, this is what folding does. Of course, it has to be complete, so if the prover and verifier are honest, the verifier should accept. That's the security property. By the way, the best way to explain the security property is through this concept. It's a new concept called a reduction of knowledge. It turns out it's a very elegant way to express what folding does. So please use this terminology of reductions of knowledge. What it does is it shows, so folding basically shows that it reduces knowledge of W1 and W2 to knowledge of W tilde. So if you know a witness for U tilde, that should imply that you know witnesses for U1 and U2. So again, we're reducing knowledge of witnesses for U1 and U2. We're reducing knowledge of U tilde to knowledge of witnesses for U1 and U2. Yeah, so I just wrote that informally over here, that if the verifier accepts what the prover produced, the prover then must know original witnesses for the original statements. By the way, I should say reductions of knowledge is a generalization of knowledge soundness, and that knowledge soundness is a reduction of knowledge to the true statement. Yeah, but more generally, you don't have to reduce to the true statement, you can reduce to more complicated statements. Okay, so we understand folding in terms of reductions of knowledge. Okay, so that's the formal property. I hope everybody okay with this, that if you know a witness for the folded statement, you must know witnesses for the original statements. That's what folding does. And then once we have a folding scheme, oh yeah, now I should say the whole point of folding, what is the point of this exercise? The whole point of folding is that actually the prover now doesn't have to produce a full proof. The prover is just producing a folding proof, which is much, much faster. The verifier doesn't have to verify an entire snark proof. It just has to verify a folding proof, and both of those things are dramatically easier than producing a proof and verifying a complete proof. Okay, so that's the reason why we like folding so much over recursion. Yeah, there's some caveats. Folding doesn't apply everywhere. There's some caveats which we'll get to later. But generally, folding is, at least if you're producing a single proof by a single prover, folding is a better way to do recursion than full recursion. Okay, good. So yeah, so I guess this part I can skip over quickly. So once we have a folding scheme, we can build a full snark from it, just like we did before. This part I think I'll just skip. Okay, so how do we build these folding proofs? All right, so how do we actually fold? Well, it turns out we need a linearly homomorphic commitment. So which linearly homomorphic commitment are we going to use? The first thing that comes to mind, of course, is Pedersen commitments. Yeah, so here we wrote down what a Pedersen commitment is. So the nice thing about using Pedersen commitments for folding is the folding proof is the proof that the folding is correct is relatively, it's not too complicated. It basically follows directly from, it's a 3 special soundness proof, and we get a very nice construction, very elegant folding scheme out of it. This is how Nova, Hypernova, and all these related folding schemes work. The problem with using Pedersen commitments in this context, though, are substantial, right? So first of all, when you use Pedersen commitments, you have to use relatively large fields. You have to use a 256-bit field, or maybe even more, so large fields. The other issue is that the folding verifier, it turns out, has to do both field operations and group operations. Since snark circuits only support one field, yeah, either FP or FQ, whichever one you choose, you're going to have to do some field emulation inside of your circuit. So that basically means that the folding verifier is not as efficient as it could be because, again, it's doing some non-native arithmetic as part of verification. That's the issue with Pedersen commitments, and of course, it's not post-quantum secure, which means that the system is not going to be binding as a result. Okay, so what do we do? What can we do instead? So the natural question to ask is, can we fold using a lattice homomorphic commitment? Yeah, and the whole point of what I want to show you is, yes, in fact, we can. This system is called lattice fold and its derivatives. But unfortunately, as with everything with lattices, there's lots of complications. Yeah, somehow with discrete log systems, everything just works as intended. And with lattices, you always have to work harder to get things to work. So that's what I want to walk through. So the benefits are now all of a sudden you're using much smaller fields, only 64-bit fields. And actually later today there's a beautiful talk by Nethermind. I highly recommend everybody go to this talk that actually experiments with lattice fold and its derivative. One of the things they show is that for reasonable numbers, itai hash is about 30 times faster than the Pedersen hash, which suggests actually that the folding prover and folding verifier could be dramatically faster than if we use Pedersen. Unfortunately, it's not quite as good, right? So 30x speed up would be fantastic, but as I said, with the minute you start doing itai hashes, things get complicated, and the extra complications eat up into this 30x potential. Yeah, so the dream is that we actually would get a 30x speed up in the folding prover. The reality is we're not quite there because of all the extra complications that come from lattices. The other nice thing about lattices is that you're only using one field. It's not like you have 2 fields as we did with Pedersen. Here, when whatever vector you're hashing, the hashed vector happens to be in exactly the same field. So as a result, you don't have to do any field emulation. And as far as we know, at least we believe, this is post-quantum secure. Okay, good. So that's the goal. So now the question is how to do it. So the first thing I have to do is remind you a little bit about how, again, I just wanted to make sure everybody's familiar. I didn't want to assume everybody knows lattices. So let me just remind you how itai hashes work. So we fix our prime. We fix a bound size, which in this case is 2 to the 16, and we have some dimension n for the vectors we're going to compress. So given a vector w, in this case, it's L infinity norm is bounded by beta. The way we hash it is like as simple as you can imagine. We just do a matrix vector product, A times W, and that's it. And you already see that W itself lives in the field FQ. The hash of W also lives in the field FQ, or ZQ rather, so we end up with only one field that needs to be supported by the circuit. So that's issue number one. The problem is this hashing, this matrix vector product is not by itself collision resistant. Of course, a matrix vector product cannot be collision resistant. It's only collision resistant when the input vector is bounded in norm. Yeah, and that's what causes all the problems, as we'll see in just a minute. Okay, good. Yeah, of course, it's linearly homomorphic, so that's trivially linearly homomorphic, so there's nothing more to say there. But it is important to remember that it's only binding when we apply it to lower norm vectors. Now, some people were asking me, or rather complaining about latticefold, saying, "Oh my God, you have to store this big matrix A in order to do all your operations." Well, it turns out that's not really true. You don't have to actually store the matrix A, just like we do in post-quantum crypto. The matrix A is often generated from a seed. What's interesting is we don't even have to use a very complicated generator. So this generator would have to run inside of your snark circuit. So we want to use the simplest possible generator we can use. And in fact, that is the case. We can use relatively simple generators to produce a and actually, that's a good question. Like, what is the most snark-friendly generator to generate the matrix A that would retain the security of the itai hash? But that's another issue that needs to be studied. Okay, and finally, so finally, this is only describing the itai hash over ZQ. Unfortunately, that requires, as you can see here, a matrix vector product requires basically lambda times n operations, and the question is, can we make that better? So how do we make that better? How do we speed up the itai hash? Somebody want to yell it out loud? How would we speed up an itai hash? Somebody has to know the answer. So what I described here is over ZQ. If you don't like ZQ, what do? Yeah, you go move to rings. Exactly, rings. Rings are our friends, right? So, so instead of working over ZQ, instead we're going to use an RQ. Yeah, that's what people were saying. So we move to a ring, and I just want to stress, like, why is it so useful to move to a ring? When we move to a ring, what happens is instead of doing a matrix vector product with the vector and the matrix over ZQ, instead what we're going to do is we're going to do a matrix vector product, except now the vector and the matrix are all elements in our ring. Since the ring has every element in the ring is represented by D elements, what we can now do is we can shrink our vector and we can shrink our matrix by a factor of D. Right? So the matrix shrinks both in a vertical and horizontal direction by a factor of D. Our vector shrinks by a factor of D. The commitment shrinks by a factor of D. And everything shrinks. Okay, so that's great. Naively, you would say, oh, that doesn't really help much. Sorry. Again, I have to state this again and again. It's very important that this operation is only binding when we're applying it to lower norm vectors. Okay, the problem, of course, the benefit of this, of course, is that now it turns out the complexity is only, well, let's see. So we can just calculate the size of the vector is, the matrix vector product is now going to be lambda times n divided by d squared, right? Because everything, I guess, what is it? The horizontal direction shrunk by a factor of d, vertical direction shrunk by a factor of d. So the number of operations is lambda n over d squared. But of course, each operation now is more complicated because we're multiplying two ring elements. If we do that using FFT, that takes roughly d log d times. So overall, we just improve things by a factor of d. Okay, so this is why whenever we use the itai hash, we're always using rings instead of ZQ. Okay. All right, so far so good. All right, so the question then is, how do we fold with the itai hash? So let's get into how actually folding works. So when you do folding, you kind of do the oldest trick in the book. Yeah, the way we fold is actually by taking random linear combinations of the input statements. So remember, we have our commitments to the witness and we have our witness. The way we fold is we take this random linear combination. So here you can see the folded commitment, the folded witness, are these random linear combinations, and immediately you run into a problem. what is the problem we run into? Remember that the commitment has to be an iti-hash of w tilde. So c tilde is an iti-hash of w tilde. The problem is, once you start taking linear combinations, random linear combinations, this w tilde is no longer short. Yes? So boom, we ran into a problem. So this basic folding method just doesn't work. So what do we do instead? So this is basically what this says. If we just did regular folding by taking linear combinations, that would no longer be sound. So what do we do instead? So so we solve it in the usual way that we solve problems with these norm bounds. We are going to do some decompositions. So the way this will work is, let's see. So we take our original vector. So we take our original statements. What we'll do is we'll break them up into, we'll do decomposition. Yeah? So suppose we have an element A that's low norm. We'll split the element A, or rather we'll write it base B. So we'll split it up into its digits. And then we'll apply the iti-hash basically to this reduced norm vector. So really, the way this works is the following. So we have our two statements that we're trying to fold. What we'll do is we'll take each one of these statements, we'll split it up into, let's say, 2 or more statements. Here in this case, it's only 2 statements. So instead of folding 2 statements, now we end up with a problem where we need to fold 4 statements. We fold these 4 statements together, and because the norms were reduced, even though we sample our linear combinations in what's called a sampling set, we end up with sufficiently low norm vectors. Okay, so random linear combinations work if we do the decomposition ahead of time. Okay, so that was easy, not very interesting. Everybody's kind of familiar with this approach. The bigger problem is the next challenge. So this basically ensures that w hat is in the right interval so that the iti-hash is committing. So far, so good. Yeah, so we got over our norm growth problem. The bigger problem is we have to build an extractor, right? So the way reductions of knowledge work is, well, you have to show that you can extract witnesses for the original statements from a witness for the folded statement. Of course, the problem is when you try to do that, the adversary could give you an arbitrary malicious witness. And the problem with this, as usual, is when you try to extract twice, what will happen is you'll end up multiplying. So here, we rewind. We get our 2 witnesses that we're trying to, from which we're trying to extract. And the way we extract is we have to multiply by this gamma 1 minus gamma 2 inverse. Gamma, remember, is the random linear combination. So now we have to multiply by gamma 1 minus gamma 2 inverse. That is, again, a high norm value. So the result is we are extracting a high norm witness, which is invalid. We're not allowed to extract a high norm witness. We have to extract a low norm witness. And this is a bigger problem. Yeah, so how do we force the extractor to extract actually a low norm witness? So the only way we know how to, so maybe it would be great if there were other ways, if anybody has other ideas for how to force the extractor to extract a short norm witness. The only way we know how to do it is by actually requiring the folding prover. Yeah, it's by requiring the folding prover to prove to prove that the original witnesses W1 and W2 are themselves low norm. Okay, so if the original prover proves that the original witnesses were low norm, that would say that basically that we can use that to enforce that, to ensure that the extractor will actually output low norm witnesses as well. Okay, so all of a sudden we're trying to do folding. We use decomposition to avoid norm growth, like trivial norm growth of the witnesses, but all of a sudden now we have to include a range proof to make sure that the extractor actually works correctly. So that's kind of painful. That's kind of the unfortunate part of this, and that really eats up into the 30x potential speed up that we get from using the iti-hash instead of the Pedersen hash. All right, so what do we do? How do we do this? So in the original lattice fold, what we did is that we use kind of a range proof. Oh, by the way, I forget, maybe I need to make it clear. What do I mean by a range proof here? So what we have to do basically is to prove, I should probably point that out more explicitly. What we have to prove is actually that the vectors, that the elements W1 and W2, which are now vectors over our ring, basically every element in that vector, all of its coefficients are small. So the norm bound applies here to the coefficients of the vectors, the coefficients of elements that make up the ring elements. Okay, I think we saw something like this in the previous talk. This problem actually comes up here again. So in the original lattice fold, what we did is we basically used a bit decomposition method to do the range proof. The bit decomposition method was particularly useful because it allows us to use a sum check to do the range proof. The sum check combined nicely with the statement that we're trying to prove. The statement was using this customizable constraint system, CCS systems. So we could encode the statement and the range proof in one sum check and get all that done at once. Yeah. So that actually introduced quite a bit of overhead. And in fact, the talk later today that Nethermind is going to give, I'm not going to steal their thunder, just come to that talk and you'll see how this compares to Pedersen-based folding schemes. Yeah. So they have a full implementation of this method. I think it's fascinating to see how it compares to Pedersen folding schemes. I'm not going to tell you. You have to go to that talk to see if it's faster or slower. Okay. What I will tell you is we can do better now. So Lattice Fold Plus is a much more efficient range proof, uses a much more efficient range proof for W1 and W2. It turns out for convenience reasons, we also changed a little bit how Lattice Fold works. So what we do, the way I described it so far is we decompose and then we fold so that the folded statement has a short norm. Rather, the folded witness has a short norm. And it turns out in Lattice Fold Plus, it turns out to be it's better to fold and then decompose to reduce the norm of the folded statement. So I thought I would just end by showing you a little bit of how the Lattice Fold Plus range proof works. Actually, how am I doing on time? Oh, wow, fantastic. So I was going to go through this very quickly. Okay, so the way this range proof works is basically as follows. Suppose we start off with a simpler problem where we just have n scalars, and we want to prove that these n scalars are in a certain interval. Okay, so they have low L infinity norm. It turns out what we do is this is kind of a cute trick. So what we do is we take this vector and then we commit to elements where we encode this vector as monomials. Yeah, so these are elements in RQ. So each monomial is an element in RQ, but it's kind of odd that literally the FIs become exponents. This actually makes sense because these are numbers between minus d over 2 and d over 2, so we can encode them in our ring. So we end up with a vector of n monomials. Now what we have to do, the prover now, is to prove two things. First of all, he has to prove that f is really constructed correctly. So f is really a set of monomials that represents f1 to fn. And second of all, we have to prove that all the exponents really are in that interval. And it's kind of a magic that this works, but the cool part of the paper is that basically these two proofs, the fact that f is constructed correctly and that the monomials, their exponents, are in the right interval, actually that can be done using a purely algebraic check that's actually really quite fast, and it's just a simple sum check. Yeah, so I would say this is the heart of the paper. I mean, if I was giving a technical talk on Lattice Fold Plus, I would spend all my time on just explaining exactly how this works. But yeah, this was supposed to be a higher level talk. So I'm going to leave it to you to maybe look at the paper and see how this works in detail. Yeah, the point is there's no more bit decompositions, so everything is purely algebraic and just using simple sum checks. So this should be quite a bit faster than the basic lattice fold method. We expect about a factor of 5 speed up over basic lattice fold. Again, if you come to the Nethermind talk, they will tell you exactly what the running times look like. So please go to that talk. All right, so okay, so there's one more complications. I'm out of time. Am I out of time? Okay. You know what? I think maybe I'll skip this. It turns out if you want to shrink the proof, there's this extra trick called double commitments, where we commit to a vector of commitments, something along the lines of what was used in Labrador. But I think maybe I'll skip the double commitment method. This turned out to be kind of a fairly technical part that maybe I'll skip here. Okay, so to summarize, basically we have these new lattice-based folding schemes. There's the original lattice fold. There's the improvement lattice fold plus. There's a third improvement called Neo that gives an orthogonal improvement to lattice fold. So we kind of have two improvements now to lattice fold, which is very exciting. The point is we can now do folding in a small field. We have very efficient verification circuits. It's post-quantum secure. It supports these high-degree constraint systems. no setup. And so, yeah, so my point is that if you want post-quantum piecemeal snarks, it looks like lattice-based folding is kind of a good way to go. And the interesting thing is, I think this is kind of one of the first times where a post-quantum snark system might actually be better than a pre-quantum snark system. So that's kind of exciting because we haven't had that before. So yeah, so I think I'll thank you very much. I'm a little bit jet lagged, so hopefully this was clear. But thank you very much, and I'm happy to take any questions.
Thank you. Thank you, Dan. We're just happy that you didn't fall.
Yes,
so
that's right.
It's all good. Any questions?
Thank you for the great talk. I was wondering, is there any bound on number of times we can fold?
Yeah. So it's a great question. So there's no a priori bound on the number of times we can fold. That is, we don't know of any attacks. The proofs, of course, kind of prove only one folding step. And then it's up to you to decide how many times you want to trust the system to fold. Yeah. But that's kind of a generic issue with recursion and folding in general. Yeah. It's a very good question. Even more than constant. Yeah, you can do. Yes. That's right. This would inherit exactly the same results. Exactly. Yeah. Yeah, but constant is not that interesting. So it wouldn't be an interesting recursive method if all we could do is constants. Yeah.
So you're saying that all folding schemes today are lacking some form of concrete security when it comes to the implementation?
And let's just say, maybe I'll say in more way than one, but maybe we'll just leave it at that. There's a lot of work to formalize. There's there's sort of inherent limitations in our ability to prove these recursive methods, having to do with the random oracle model. In fact, Ron's talk from yesterday kind of shows that maybe these are not just limitations. Maybe there's more than limitations here. Yeah. And so that's the world we live in.
Thank you. More questions? All right.
Amazing work. I wanted to ask you mentioned at some point in the extraction that you're using rewinding, and I want to ask about the compatibility with post-quantum, or is it post-quantum in the sense that we don't know, that it's classically secure and we don't know an attack?
Yeah. Oh, it's the latter. So it's exactly it. So yeah, look, there's a lot more work to do here. Absolutely. So let's see. So what you're asking is if we're trying to let's see, if we're applying rewinding, how does rewinding play with the post-quantum world? And of course, how does rewinding play with a quantum random oracle model? That's the issue. How does it work with a quantum random oracle model? Yeah. So there's more work to do here. So for sure, that would need to be analyzed as well. So it's a very good question. Yes. Yes.
The idea is to try and get the proof into a margin.
Yes, actually, I just talked to Kevin. Actually, so they're like his goal in life is exactly to build a lean proof for Fermat's last theorem. Yeah. That would be amazing if he can do that. They're not quite there. That's probably years away. But yeah, then you could build a snark out of it, and you can print on your T-shirts a proof of Fermat's last theorem. Yeah, absolutely.
All right, let's thank the speaker again.
Thank you
so much, Dan. Thank you all for your patience. I know we're all hungry. Let's go for lunch, and we'll be back at 2:50.